So I'm going to kind of walk you through a little bit of the way I discovered this information and the way I came across it, my logic through it, and the path I took. And if I walk you through the same path I took, you'll see that it actually is a very simple path. It's a very simple way of thinking. It's very fundamental and very simple axioms that just needs very little adjustments in our current physics and science and so on to generate just a little bit of a different picture that opens doors to a whole new way of being.
I'll give you an example. Spiritual people tend to think in terms of infinity, that like this infinite potential, you know, that all things have infinity within them and all this. And the scientific community tends to think in bounded, closed systems of finite, you know, rational concepts. And so the two don't agree, typically. The chasm even goes deeper. I think the deepest of that chasm is the difference between female and male. Women typically think in terms of continuum, in terms of curvature to infinity, like infinite possibility. Everything is okay, honey, right? And man thinks, in general, have a tendency to think in bounded state, you know, finite, highly logical systems. Here lies the problem. The idea that things can be isolated, that you can, you know, put something in a box and assume that you can analyze that thing ignoring everything else that's going on in the universe. As if you've isolated that box from the rest of existence. And more, as we advance in our technology and in our physics, we realize that that is just not the case, that that is not actually anything that exists in nature, and this artificial way of analysis does not lead to accurate description of the physics of our universe. So how do we deal with it? In one way, what we have to do is start to get what I call a holistic view of the universe. The whole thing. We got to start with a concept in which we understand the whole structure a little more before we start looking at the part. That is, we got to make we got to have a clearer picture on how the structure of embedded system exists in our universe before we try to identify what the part may look like. Otherwise, it's similar to like taking a Boeing 747 and breaking it down to the smallest piece and then giving that piece, which might be very tiny, right, to an engineer and saying to the engineer, okay, what did that piece come out of? Could be problematic.
It really started when I was approximately 9 years old. I could have been 10 or 9, but I remember very distinctly this first lesson at school. And interestingly, I found that many other people had the same kind of hick when they got into this first lesson. It was the first lesson in geometry. And the teacher went to the blackboard and said, today we're going to learn about geometry, and the first lesson in geometry is dimensions. And I got really excited because I had all these incredible world that I was living in my head, and I had all these interaction with all these other dimensions in my head, and I thought, oh my God, this teacher is going to talk about this for the first time ever. I'm going to have an adult that talks about this, and I got really excited about it, and I got so so disappointed. It wasn't at all what I expected. The teacher went to the blackboard and made a little dot. And he placed beside the dot dimension 0, 0D, and said this is a dot that represents a dimension that does not exist. And I was already confused. I'm like, oh my God, this is not looking good. I'm probably going to fail this class because I could see the dot. And he was telling me that it didn't exist. And so already I had a problem with that fundamental axiom. And really, this is so crucial. This is so crucial to our understanding of reality. This very fundamental axiom of dimension bleeds into advanced physics, advanced mathematics, and all sorts of sciences, and really changes the picture of the way we see things if, it's not accurate. So I didn't know all this, but I thought, well, I can see the dot, but if you say it doesn't exist, I'll just go with that. And then he said, well, because it doesn't have volume, it doesn't exist. So if you put a bunch of dots together and make a line, you still don't have volume. We'll call that dimension 1. And that doesn't exist either. And, I just kept on going with it. And I could see the other kids in the class were a little bit puzzled about what was going on. And then eventually, he put 4 lines together to make a plane, called it dimension 2, and said that didn't exist either. It still didn't have volume. It was a 2-dimensional flat plane. And then he did something extraordinary, something miraculous, something that even puzzled me further. He took 6 planes, put them into a cube, and called it 3D, and said that dimension exists because it has volume. And I could see that everybody was like, okay. There was a problem in logic there. There was a problem there because if you have a dot that doesn't exist, that makes a line that doesn't exist, that makes a plane that doesn't exist, then you cannot get existence out of 6 non-existing planes. So what you get is some unknown feature that could only be called non-existence to the 4th. Not existence. And so here, fundamentally, there's an issue. And that issue has to do with our understanding of how reality emerges, how dimensions are generated, and how we can get existence, reality, atoms, objects, things in space, and how we solve the equations that describe how these things in space come through, how they get here. That is very fundamental. I didn't know all this at the time, but I knew that this principle that was being demonstrated to me was not quite correct. There was definitely improvements that had to be done to it. And I really felt like I didn't want to spend another day going through my life not knowing what a dimension was. So I decided I was going to solve this. And, I had this long bus ride going all the way back home. It was like an hour and a half from that school. And the reason for that is because I kept on getting kicked out of the schools that were closer to my home. So I kept on having to go further and further. And somebody told me, a physicist told me once, that I was furthering my education that way. And he was right, because I had all this time to think in the bus. So I was in the bus and I was thinking about this problem, and I decided I was going to solve that problem before I got out of that bus. And I didn't realize that this problem had been discussed and worked on by many philosophers throughout the ages and so on, all the way down to the Pythagorean schools. I just wanted to solve it right there and then. And so I was thinking, and the bus was getting fuller and fuller, and I was getting hotter and hotter, and it was really, becoming uncomfortable. So I closed my eyes, and in my mind's eye, I escaped the bus so that I would feel more comfortable. And I start to see that the bus would, as I rose above it, the bus would become a dot. And then I rose further, and I saw the earth becoming a dot. And then I rose further, and I saw the solar system becoming a dot. And I rose further again, and I saw the galaxy becoming a dot. And then I started to fly back into the galaxy, into the solar system, back to the earth. And I located the bus I was in, and back into that bus, and back into my body. And I opened my eyes, and I looked at my hand, and I thought, oh, maybe I could fly into my hand. And so I closed my eyes again, and I thought of flying into my hand, and I saw that inside my hand would be dots that are called cells, and then inside those cells I would see millions and millions of other dots that are called atoms. I probably didn't even know what an atom was at the time. And I continued in, and I saw, the nuclei of an atom that was made out of smaller dots, and then again smaller dots, and so on. And I thought, and then I got it. I had this moment of illumination. And then in the bus, going back from school, oh yes, the only solution to this riddle, the only way you can solve this, the only way you can, the only way you can visualize, understand dimension, is if you'd make the exact opposite axiom right from the beginning, which is that the only thing that exists is the dot. So here, within the dot is all dimensions. Within the dot, we have all the structure of space-time. Within the dot, all possible other dimension became in existence. That's the way I saw it. Meaning that if we continue to divide the dot, we could find smaller and smaller and smaller dots, and those would be like scales of dimensions. And that the only thing that exists is the dot. And it is only from your perspective that you define the scale at which you observe those dimensions. I mean, that was a completely different view, definitely. And I thought, well, if the dot, if zero dimension is all dimension in one, then that would mean that everybody that I'm looking at in this bus has all the dimensions, all the structure of space-time compactify in every dot. I mean, I wasn't thinking in terms of space-time, but I was thinking in terms of fractal dimensions. I didn't know fractals, but I had defined it in my head. And I got really excited. I was walking on a cloud. I got up in the bus and I didn't know what to do. I was like, oh my God, I think I got it. Everything is a dot. Every dot has infinity within it. Everything can be divided to infinity. And there's dots to infinity, infinitely big, infinitely small. We're living in a big dot that has little dots in it and little dots in it. And I was seeing dots everywhere. It was really exciting. And I, when you have a revelation, you want to tell someone. And so I ran home when I got out of the bus, and I was waiting for my mom to get back from work. And when my mom came in the door, I'm like, Mom, I figured out something at school today. It's really exciting. And then I started to tell her about this. And I'm telling my mom, you know, I think you have a dot inside of you that has all the dots and infinite dots inside and all this. And my mom is looking at me with a look of despair. The look of an Italian mother in despair. There's a force in that hasn't been calculated yet. And she said, anyway, right now, I just worked 8 hours, and I don't feel infinite. And when she said that, it rang a bell. I mean, she made a point. She made a very important point. I stopped and I had to think about it. It's like, well, if it's true that infinity is compactified in every point, how is it that we have finite boundaries? How is it that things are not just falling into each other to infinity? And how is it that things exist? How do we define those boundaries? How do we have a finite space in an infinite potential? How can that be together? I didn't know at the time, but actually I was tackling one of the fundamental difficulties in advanced physics. The difficulty of dealing with infinities and singularity, which is really the crux of unification at this time. But eventually it came to me. If we want to be able to understand the fundamental structure of creation, and that fundamental structure implies or involves infinities and finite boundaries all at once, we have to find a way to bring these two together, to understand their interaction, to understand how that works. And if we did that, and if we did so, we would have the key to universal forces. We would have the key of the powers of creation. It would be very powerful. It would be powerful for philosophical reason, and it would be very powerful for application to advanced science and technology. Now, it took me a while before I realized that there is a direct and intricate link between infinities and finite boundaries, and how to understand them and how to demonstrate it. I found eventually that the key was geometry, the very thing that got me going in the first place in my geometry lessons. And I'm going to demonstrate to you right now, in very simple terms, that you can create infinities in the confine of a finite boundary. That these are not opposite concepts, but they actually are complementary. We're going to generate a finite boundary we're going to call a circle here. And this circle could be a 3D sphere that contains a very specific space. And in that sphere, or in that circle, we're going to put a triangle, an equilateral triangle. Now, the universe is polarized. And the reason why things are polarized is because they spin. Okay, things in the universe are polarized because they spin. Angular momentum creates shafts of rotation that generates polarity. So if you have polarity, then you can accurately have a reverse triangle in that sphere or in that circle. Now, right away, we have one of the most common ancient symbols that we find all around the world. It's called the Star of David, or the Seal of Solomon, or the six-pointed star. We'll talk about this later on in the presentation, but just take notice of it. Now we can continue to add triangles. And now we get smaller stars, baby stars of David. Okay, baby six-pointed stars. We can continue to add other resolution of stars by adding more triangles. Again, smaller stars of David. Every time we create a new resolution, we can define a very specific boundary. This is very important. And here we find a third boundary, so smaller and smaller sphere. We can continue to make smaller and smaller resolution of this geometry. And in fact, if I give this to my computer as a computer code, and I got it to make geometries maybe 5 resolution deep, and then zoom in, and then go 5 resolution deep again, and then zoom in, and then keep doing that, it would continue to do that to infinity. As long as the computer had power and chips would keep working in there, it would continue to make boundaries for thousands of years. However, I would never, ever, ever exceed the first boundary that I've set for myself. Within a finite system, I've demonstrated to you right now that you can create infinite numbers of division. Infinite numbers of sets of information. In a boundary is the possibility of infinite division. And thus, infinities and finite structures are complementary. Why is this important? Well, if you were taking these principles and applying them to yourself, you could start to visualize, you could start to imagine, you could start to experience that maybe within the confine of the finite structure that you're in is the potential of infinite division, the potential of infinite amount of information. Philosophically, that has a very powerful impact on someone's consciousness. It just happens to be very similar to what many of the masters that have walked the earth have talked about. That within is God, the kingdom of heaven, infinite boundaries, and so on, or infinite potential, and so on.
So all of a sudden, you're starting to have a mechanical and mathematical understanding of the infinite nature of your existence. It's no longer just a metaphysical concept. It's no longer a belief or a dogma. It's actually a mathematical equation.
It definitely has an impact on science. Why does it? Well, I'll give you an example. When we discovered biological cells, we had microscopes that were at the maximum of the power of amplification that we could get at the time, and we thought, my God, this stuff is so small, it's gotta be the smallest thing that the universe does. And then we discovered an atom. And there's billions of atoms in every cell. That is extremely small. And we thought, oh, that's gotta be the smallest thing the universe does. And then we discovered protons and neutrons in the center of the atom. We discovered the nuclei of an atom, and we thought, that is so small. That's gotta be the smallest thing the universe does. And then quarks and so on. And what I'm saying here is that every time we find a new boundary, we think, that's it. We found the fundamental structure of creation. The universe goes to that size and then quits. That's it. I'm done. I'm not going smaller. This is way small enough. We did exactly the same thing in the other direction. Right? We thought, oh, you know, at first we thought the Earth was the biggest thing, and then we thought the solar system was the biggest thing. Then we found galaxies. Oh my God, that's got to be the biggest thing, right? And then we found superclusters and so on. Now we're at universal size, and we think, okay, that's it. It stops there, right? Well, what if it doesn't? Now, what does it mean to the physicists? Well, it means that we've been building accelerators to break particles into smaller and smaller and smaller bits. And now we're at like billions of times smaller than an atom. And we're calling these accelerators, I mean, they're serious pieces of machinery. The one that's being built in Switzerland right now, the Hadron Collider, is costing $300 billion. It took 5 countries to flip the bill for that one. And now we're looking for the X bosons and mini white hole black holes. And I'm like, well, at that point, you're dividing the vacuum. And basically, what I'm saying here, maybe instead of looking for a fundamental particle, we should start looking for a fundamental principle of division. And that's what I came to, is that instead of looking for a fundamental particle, we should start looking for a fundamental pattern of creation. Because if we understand the pattern, then it doesn't matter at which resolution we are observing the identity. We understand the principle behind the identity. Now we have the key to creation. Me in Georgia Tech. I'm at Georgia Tech, Department of Physics, with the director there and other physicists. And this is an impromptu private meeting discussion with those guys. And basically my sponsors at the time brought me there to measure up with the biggest and most respected physicists, some of the biggest and most respected physicists in theoretical physics. And, you know, I'm there and they have equations everywhere and we're talking about things, and it's a very small meeting, you know, but there's a few students and there's a bunch of physicists there, and there's me. And the only thing I got with me is this book. It's called Gravitation. It's like the Bible of relativistic physics. And it's called Gravitation because when you pick it up, you know, you can really tell gravity is acting upon things. And I was, you know, going through the equations with them, and I'm talking about all this, and I'm really, you know, going through it with them, and I can see that there's a certain amount of irritation, and there's a certain amount of impatience with me because I'm asking very simple, fundamental questions. And everybody there is doing very advanced, you know, string theory physics and all this. And, you know, I'm always going back to like some fundamental things. And they're like, my God, what is this guy doing here, kind of deal. And, you know, and so at one point, I pulled out my book, Gravitation, and I said, okay, after all these equations, which is a few thousand equations, on the metrical structure of space and then applied to the universal size and so on. The model of our universe at this point, and correct me if I'm wrong, is that the universe is expanding like a balloon. And I opened the book on page 219 and I pulled it out and I said, here's the picture of what we believe the universe is doing right now. It's expanding like a balloon, and and the balloon has little pennies glued to it, and the pennies represents galaxies. That's the standard model. And the galaxies are moving away from each other as the balloon expands. And everybody's like, yes, Nassim, where are you going with this kind of deal? Like, if you don't know this, go back and study, come back in a few years. And at one point, well, I'm saying, well, okay, I understand this principle. However, I have a question. Out of all these equations everywhere, what I want to know is, where is the equation that represents who's this guy? And the whole room became really silent. And I could see that in the look of the students and the other physicists, that there was a look of despair and stress, because sweat was a little bit beading. And I could tell that they got worried, because they thought, oh my God, this guy, he might just start talking about God. And we're at Georgia Tech in the physics department. We can't do that. and I reassured them very quickly. I started to draw, and I said, well, let's draw the rest of the guy. And what I'm trying to point out here is that in order for the balloon to expand, then the lungs of the person that's blowing into it have to contract. For every action, there's an equal and opposite reaction. Okay? One of the first laws of physics. So if our universe is expanding, then there must be something contracting. There must be some compression happening in order to get expansion. There must be a feedback between the expansion and the contraction. And that was my first clue to the relationship between the gravitational field and the electromagnetic radiation. And as well, it applied to my experience in life, because really this is all based on my experience in life. When I was 11, I started meditating. My family came in contact with a young master of meditation that was 14 years old, and I was 11. And he taught me how to meditate. And when I meditated, it felt like I was turning my senses inwards and going towards the center of my existence. I was going towards the middle of my being. And I came, out of that, I found a logic in which there was an internal universe and an external universe. There was something going in and something going out, and the two generated boundaries. And that boundary is what we experience as reality. The thing is that in our society, the tendency is to spend a lot of time analyzing what's out and very little time analyzing what's in. Not only in our, social morphs, but as well in our physics and the way we do things. We explode things. That's how we build technology. Our concept of advanced technology is to put a bunch of fuel in a cylinder, put a bunch of people on volunteers on top, and light the bottom and see if they survive the experience, It's all based on expansion, on explosion, on radiation. Very little is based on contraction, on going towards the center, on implosion. And to me, there had to be a direct relationship. So I was really pointing that out. And now we're going to go back to when I was younger. And when I was thinking about that, I could see that this relationship would generate some kind of field equation, would generate some kind of metrical space that I could describe in mathematics and physics that would resemble more like a feedback of creation. Well, just happens that the fractal structures that I was talking to you about when you divide space are based on feedback equations.
If you were asked to point at something in the universe that connects all things, what would you point at? What would it be? If you had all the universe, everything you see, and I asked you, find me something that connects all things, because you hear that a lot in the spiritual world, and you know, from masters that in ancient times and so on, that everything's one, right? But how? If you don't tell me how, then it's just a concept. It's just a dogma. You got to tell me, how is that possible that everything is connected? Like, you got to explain that to me. So, what would it be? Space. Very good. Very good. Space is everywhere. It's between galaxies, it's between universes most likely. It's between stars, it's between planets. And at the atomic level, the space is extremely high. Atomic structure, all of your reality is built out of 99.999999% space. So everything you say is so solid, is so real, that you think of as your reality is actually mostly space. And it's oscillating, and the oscillations interact, and did you know that you actually haven't touched anything at any time, anywhere? Nothing touches? Nothing? The densest atom is like, a molecule is a, diamond molecule. If you grew one of the atom in that molecule, the other one would be 2 football fields away. If the one you grew was the size of an orange. That's how much space there is in between them. When I touch this podium, my atoms in my hand are not anywhere close to touching the atoms in this podium. If they did, there'd be fusion, there'd be all sorts of gamma ray emission, there'd be some serious issues. There's large distances at those scales. All that's happening is that there's a little electromagnetic field here that's not in phase with this little electromagnetic field, so can't get through it. But if those were in phase with those, my hand would go right through it. No problem. Question of phase. And then the space inside the atom is 99.99999%. So maybe we should pay attention to the largest percentage instead of the smallest percentage. We spend a lot of time paying attention to the 0.0000001% that we call matter, and we spend very little time paying attention and trying to understand the 99.999999% of the space. So maybe instead of matter defining the space, maybe it's space that defines matter. And I start to realize that. You all following me? This is a fundamental change in consciousness to actually go in the world and first of all realize that you're mostly space, and that maybe the space is defining you instead of you defining it. Space is not empty, it's infinitely dense. But because it's infinitely dense, then everything cancels out and it looks to you like nothing. infinite mass. Meanwhile, we're floating in this. That would mean there's infinite amount of energy in the vacuum. And we've got a whole bunch of people on this planet going, dude, there's not enough energy for everybody. What are we gonna do? We got a war for it. So nature is giving us all the power we have today already. Right? At its most fundamental level, this is given. It is already free energy, if you'd like. What we need to figure out is how to extract it at its source. How to extract it before it's produced the material world.
I realized something very important for the evolution of the thoughts I was having. I found that present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite, if not removed by renormalization. Now, renormalization is kind of what they tried to do to me at school. It didn't work so good. But what it means is that when physicists start to look with the tools of quantum theory at subatomic particles and nuclear interaction and all this, they found that in order for this to be happening the way we see it happen, the vacuum density at the quantum level would have to have infinite amount of energy. That was the result of the equations. Well, equations that ends with infinity are very uncomfortable for physicists. There's two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, and that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there, it doesn't matter. Okay? That's one kind of... Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and like avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they call renormalization.
That is, you try to find a constant that you can apply to it so you get a finite number. So in this case, and they did that to quantum theory in another way as well, they use this constant. It's called a Planck's distance. You can think of the Planck's distance as the minimal amount, the smallest wavelength that the universe can do, calculated from our physics using, electromagnetic theory and gravitational theory and so on. This is what we calculated is the teeniest thing that the universe can do. It's 1.616 multiplied by 10 to the minus 33 centimeters. So it's very, very small. Extremely small. Billions of times smaller than an atom. So, do I believe this is the smallest thing the universe does? Absolutely not. However, I believe that this is the fundamental boundary condition that defines our relationship to the universe. That is, from our boundary condition, from our scales, this is the smallest thing we experience.
Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance, bitty teeny point, and they stacked them into that cube. And then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, following it. It's an extremely large number. When I'm dealing with a number that large, and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way, but never mind that, then you still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particles and atoms? To me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. If this is true, then if we look at a large scale in the universe, we should start to see very specific divisions. We should start to see structure. If the vacuum is dividing under very specific structure, then we should be able to see it. We should be able to calculate it from what we observe. So we decided to write a scaling law. What we did is we took the radius of objects, okay? And so here on the in the x-axis is the radius. And here is the frequency of these objects, the fundamental frequency of these objects in hertz. And the energy level of the object is pretty well described by its frequency. So you could think of its energy level as well. If you take the size of the universe, that is, if you look at the way the universe is expanding, you can extrapolate its size. And if you look at all the matter that's in the universe, when you place that amount of density, when you place all that matter in Einstein field equation, the result is that the universe is too dense for light to escape it. That is, we live inside a black hole. And, you know, that was expected for me. I thought that earlier, and then I realized that as well from my own calculation before, and I thought that would make sense. Because remember, I was thinking that if for every expansion there's an equal and opposite contraction, then everything can be divided to infinity, then everything would have infinite density at its center. Everything would have what we call singularity at its center. And so I thought everything is just a different size black hole. And so I wasn't surprised about this. So we placed the data point for the universal, the 10 to the minus 17 is the universal frequency based on our calculation, and the radius is 10 to the 28. And then we place the next data point for the for quasars. We're taking average size and frequencies of quasars. This is a very large scale, so it's acceptable. And we place the data point. And it surprised us. It was a fairly good linear progression from universal size. Then we place the data point for galactic centers. So we're getting smaller in scale. And again, an average galactic center oscillation rate and radius. And we place the data point, and again, linear progression. Then we place a data point for solar dynamics, stellar dynamics, and we got a linear progression again. That was astonishing. I mean, there is nothing in standard views that would predict that, other than the view I was getting that the vacuum is dividing itself under very specific structure boundaries. Then we went all the way to the atomic level with the radius and fundamental approximation of frequency for X-ray emission. And we got a data point that was a perfect linear progression again, but this time across the boundary of quantum theory into the atomic level. So now we went from cosmological object to quantum theory level. And this is one of the fundamental fractures in our current physics. Quantum theory and relativistic physics don't agree. They don't work for each other. So that was really exciting. And then we went all the way down to the Planck's lengths and placed the Planck's length data point and at 10 to the minus 33, and sure enough, the progression was perfect. The other thing we noticed is that if you take the distance between the data point, which is kind of nice, it's sweet, and you divide them, you always get very close approximation to the phi ratio. The phi ratio is 1.618 and is, and goes to infinity. It's typical to find it in nature everywhere. You find it in flowers, in shells, in pine cones. You find it in the way tree divides. You find it in your body. There's a phi ratio between the end of your finger and the second part of your finger, and there's a phi ratio between the second part and the third part and your hand. Relative to your fingers, and then your fingers and hand relative to your forearm, and your whole body is built like that, and so on. And so you find it in nature everywhere. So to find it on a scale that's so large was very exciting, because it supported that this would be something that nature would naturally do. That space, that the vacuum would naturally divide itself under these very specific fundamental mathematics, because we observe it in nature everywhere. But if you actually add a data point for the biological resolution, what I call the biological resolution, that is the size of the sphere of our cells and their frequency level. Now, this research has shown that there's definite resonance match at approximately 10 to the 11 for the frequency of lipoprotein of the boundary of cells. So that means the cell's boundary, all right, the surface of cells in the biological level oscillate at 10 to the 11 hertz. I mean, that's a massive oscillation. And it's funny, because when we think of biology, we always think of some really kind of glooby, kind of blobby thing that's moving really slow, right? But actually, the surface, when you look on the surface oscillation of these cells, it's very intense. A lot of energy. And it just happens that if you take 10 to the 11 hertz and you take the radius of a cell and you apply that much energy into that radius, if you solve that with relativistic physics, the cell obeys the Schwarzschild condition. That is, the cell obeys the condition of a black hole. What I'm saying is that we're still dealing with the same fundamental dynamics, even at the biological level. And certainly, there's not any biology in Einstein field equation, and there's no biology in quantum theory. And you know, this link to biology has been looked for a very long time. Well, we were happy to find that if you place that data point for the biological cells on the graph, it would bisect the graph approximately in the middle of the graph. That is, the biological resolution is the link between the large and the small. You are the data transfer boundary from the extremely large to the extremely small. Isn't that what you do? You gather information and transfer it to your internal self, which in this view has infinite boundary potential. Thus, you're transferring that information through your boundary to the infinite of the universe within yourself. And as you start to see yourself grow into that world, your worldview, your way of being in the universe, the way you are, how you are, completely changes. Because you start to see the importance of your observation. You start to see the importance of your interpretation of the field and what you are feeding the universe. Instead of seeing yourself as an insignificant little dot that means nothing to the universe, you start to see yourself as the center of creation. If you have come to these conclusions, you must have come to these conclusions finding out that everyone else is the center of their universe as well. And thus, we are all equal, and we're all one.
You are in that mechanism. You are part of this conduit of information of the vacuum that goes from infinitely big to infinitely small through you. And as it passes through you, it picks up your specific interpretation of the universe and feeds it to the infinity of all things, so that your participation is counted. Do you start to get a sense of your responsibility? And so there, you know, we start to feel that connection to all of the scales. But how do we get that feeling of that connection? Just a little side note on philosophy. We get that feeling of connection not by trying to connect with infinitely big. People say, I can't visualize that. Well, that's because your senses are fairly limited. But you have the infinitely small within you. So through that direction, you can connect to infinity. This is why most of the masters that have walked the earth have said, go within. The kingdom of heaven is within. You know, the Buddha is within everything. The Bindu point is within everything. And it's your connection to all knowledge. Then that means that our universe is driven by the vacuum, that the space between you and me connects us. That the information that is in the space divides in very specific scales. And those scales makes up all of our reality. And that we're part of those scales. You guys are following this? Instead of matter being some kind of entity that comes out of nowhere, matter is just the result of the division of the structure of space itself. And you are interacting with that structure every day, every second, every billionth of a second. We know that all the electrons and positrons in your atoms are going appear, disappear, appear, disappear, appear, disappear in the vacuum. Every time the electron comes out, it's learning about your experience and then feeding it back to the vacuum. And learning about your experience and feeding it back to the vacuum. You are informing the universe. You are informing the universe about your specific point of view on the whole thing. And I can demonstrate that mathematically. And that's why people in the spiritual world are saying, you create your reality. Okay? The part that's missing in that statement is the other part of the feedback loop. A fractal is a feedback. The other part of the feedback loop is that reality is creating you. The vacuum is defining your existence. So, because you know what? If we all created our reality independently, we would never meet. We'd all be alone in our own little universe we created going, where did everybody go? We'd be really bored because we'd create exactly what we want every time and like, right? And so, but that's not what's happening. You're feeding information to the vacuum, and since the vacuum connects us all, it has the information of everybody in it, and it's feeding you back an experience, right, that's in coordination with everything else. So that there's a consensus reality. So that one being cannot overcome all the scales. So that one person cannot say, oh, you know, today I'm kind of hot. Let's turn off, let's cool off the sun. And then the poor guy in Alaska is like, dude, it's cold up here. Right? But there is scale relationships. So the idea of the butterfly analogy, right? The butterfly in Africa that bats its wings and it makes a hurricane in Florida, right? That's found in many literature on complex theory, on the chaos theory. That concept is only true if you put it in the context of scales. You all following me? Like, meaning that if the probability of a butterfly flapping its wings in Africa producing a hurricane are really, really, really low. Actually, almost non-existent. Why? Because you'd have people in Florida going to Africa with shotguns going, brah! Don't you move those wings. Right? But maybe if you have millions of butterflies all moving their wings at the same time, now you got something going, right? So the morphogenic field, we're all connected. If we're going to move forward, we got to bring enough oomph to the system so that it can modify, right? This is actually why I talk to people, right? We have to move together. It is a consensus reality. And it's really important for people to understand that, because then, first of all, you take responsibility in what you're feeding the vacuum. But as well, you realize that if it's not all going exactly how you want it to go, is because you're embedded in a morphogenic field and you're interacting with all the stuff that's going on in it. You're all following that? So, you know, be kind to yourself.
But beyond the philosophical views, the fact that the biology would fit on this graph, the fact that we could start to see the information feedback loop between the radiative side and the contractive side starts to open a whole new field of physics. For 20 years, and you know, I've been saying this for a long time, I've been saying that information doesn't just flow into black holes, but flows out of black holes as well. And I got in a lot of trouble for that. To me, it was clear a very long time ago that if this was true, then the center of all galaxies had to be black holes. So I predicted that, and then eventually they found that that was the truth. And although I got in a lot of trouble for saying that early, and so on. And so I started to see the infinite potential of everything present in everything.
But you know, when I wrote these equations, there was an issue. Why? Because, you know, I've got an atom in there that I'm saying is a black hole. Is the atom really a black hole? In very simple mechanical equations that I'm going to show you right now, I prove that the atom is a mini black hole. And how did I do that? Well, I looked at it this way. I said, I'm not going to do like everybody else and ignore the density of the vacuum. Okay? I'm not going to ignore the most intense, the most energetic, probably the source of everything thing that we found in physics. So I said, inside a proton volume, right? The proton is like, let's say you have a simple hydrogen atom, you have a little proton, is the nucleus of the atom. It's very, very, very tiny in the middle. I said, inside there, how much volume is there? And so I calculated the volume of a proton. It's 10 to minus 39. Depending on which radius you take, it's an approximation. 10 to the minus 39 centimeter cube. And I said, how much of this energy that's in the vacuum is still present inside the teeny weeny beady proton? And I made the calculation, which is pretty straightforward. And the result is 10 to the 55th grams within a proton volume. There's still 10 to the 55th grams inside the volume of a proton. Where did we see that number? The mass of the universe. The mass of the universe. Now remember our assumption, remember our statement? The vacuum connects all things. If that was true, that would mean that you'd expect all the information of every proton in our universe to be present in each one of them. And that's exactly how the math came out. Isn't that cool? This is actually the mathematical evidence, I'll call it for now, that everything is one. All right? Now, no longer just a concept, no longer a dogma. Now, it's a mathematical, physical evidence. Is everything in the universe just smaller division of singularity? Singularity comes from the word singular. One. Are we only observing division of the one? Wow, this is starting to sound a lot like ancient texts and, you know, all these prophets and all these masters that have walked the earth that told us that. Maybe we should have tried applying that to physics. This is all nice, you know, this 10 to the 55th gram per proton volume. Remember, 10 to the 55th gram is enough to make the whole universe a black hole. So obviously, if I take all of that as the mass of the unit of the proton, no doubt the atom is a black hole. But actually, how much of that do I need to take? Very little. In fact, if I only use 10 to the minus 39%, a very teeny, weeny, beady little amount of 10 to the 55th grams of energy, the proton becomes a black hole. The atom is a black hole. And I'm saying that the vacuum is feeding all atoms. That the material world is basically 10 to the minus 39% of the energy of the vacuum. It's just a little beady weedy leak, teeny weeny leak of the vacuum. And it makes up the material world. You all followed this? So imagine if we tap this energy that's in space everywhere, we don't even need to tap anywhere close to 10 to the minus 39% of it. You know, if we tap if we cohere that energy, get it to work with us just a little bit, just a teeny weeny bit, we produce enough power to power our whole planet for thousands and thousands of years. We can produce enough power to create gravitational fields, gravitational drives, travel across our solar system, travel across our galaxy, probably go from one galaxy to another or even one universe to another. We free our society from the bounds of being stuck to the surface of a planet, which is not a really good place to be. Just isn't. Cosmologically speaking, surfaces of planets are highly unstable. They don't just hang out because there's people on it. Our atmosphere is equivalent to like if you took a billiard ball and put a little shellac on it. That's about the thickness of our atmosphere. And the earth beside the sun is like a little grain of sand. A teeny weeny grain of sand. And one of those big sun flare comes out in the right place at the right time and and everybody in the solar system goes, huh, what was that? Oh, that was Earth's atmosphere. All done. Next thing you know, it looks like Mars. Right? So, never mind, you know, asteroids and comets and all the rest of the stuff. Right? So there is typically a cosmological time period in which a civilization like ours has to figure out how to get off their rock. And if they don't on time, well, you know, on to the next round. You see what I'm saying? This is a fundamental step that a civilization must do. And we are at that point. We are at that moment in our evolution where we must understand these more fundamental principles of the physics of the universe that includes the philosophy of the universe, the spirituality of the universe, the connection that connects us all, and understand how it works and apply it in our technology so that we can actually, literally ascend. So, after all this rant, if I use 10 to the minus 39% the mass of the mass of the vacuum to make the atom an uni black hole, all of a sudden my atom is a heck of a lot heavier than the atom that's measured in laboratory. So the mainstream is really not happy with that. You can imagine. In fact, my atom is 10 to the 39 orders of magnitude larger than the standard proton. So, you know, you would think, oh my God, it's got to be wrong, right? 10 to the 39 orders of magnitude wrong. Right? Well, the first thing I did, I said, well, if I'm that wrong, this, you know, it shouldn't work in a scale. So I took a scaling law. This time I took the mass against the radius, and I put all the objects in the universe I could find. You know, universe, this is the Planck's mass, the Planck's distance, and then, you know, galaxies, quasars, the sun, the earth, pulsars, and this is the Schwarzschild proton, this is the black hole proton, and this is the standard model proton. So, you know, this is straight off data. This is not really debatable. Obviously, this data point is in the wrong place. Why is that? It's because our way of measuring the mass of the proton, and just so you know, in physics, mass has not been defined. They don't tell you where it comes from. Right? Is to knock the proton out by shooting particles at it. And then it pops out of the atom, and then we make a measurement, and we assume that the proton was the same mass when it was in there. Well, you know, when you've disturbed the system, you probably don't get the right data. The key is the strong force, dear one. What is the strong force? When we found protons, we found that they were positively charged and that they would repel, just like two magnets of the same charge would tend to repel. And if they're strongly magnetized, you can't get them close together. So imagine protons squished in a little nucleon atom with the same charge. How can that be possible? When we found that, we were like, oh. And since we didn't have black holes, Einstein had just finished his equation that predicted singularity, but everybody thought that's impossible, right? They said, okay, they must, and so gravity could not be strong enough. We didn't have singularity black holes, so they said, oh, there must be a force we don't know about. We'll call it the strong force. And we'll make it exactly the amount of force necessary to force the proton together into the nuclei. How convenient. But nowhere was it given as a mechanism of this force. That is, where did this force come from? Where did the energy come from to produce that force? It was just thrown in there as a fudge factor to squish the atom nuclei into existence. Later on, and they calculated it had to be very, very strong. Later on, they realized that the proton has little bits inside it that are even smaller, called quarks. And now the quarks are charged, so they now needed an even stronger force to squish the quarks into the middle. Now that's embarrassing. You can't call it the strong force. So they got artistic. They called it the color force. And so the color force was deemed to be infinitely strong at the quarks level. Like that, you know, if they found anything smaller, they had infinitely strong force to deal with it. And that this strong, infinitely strong color force was mediating force to the proton level using gluon particles. Gluon. So that's when I asked, who's making the glue? Because nowhere in this whole scheme did they say where the energy come from to produce an infinitely strong force. But if you have an infinitely strong force confining to the center of a particle, what do you have? A black hole. If you ask a physicist how strong is the strong force, they'll say, we can give you a ratio. If gravity is 1, then the strong force is, guess what? 38 to 39 times stronger. Exactly how much my proton is off by. Right? So I said, well, you know, in my case, I'm accounting for the energy necessary to produce the gravitational force that confines the atom. You guys don't. So obviously you guys are off by 38 orders of magnitude. It's not me, it's you. I call that physics as you go. They did the same thing with the universe. They found their equation only predicts 4% of the universe, missing 96% of the universe. Instead of revising the equation, they said, we'll invent dark matter and dark energy. Throw it in there in the right percentage. Look, the equation works. Must be there. Physics as you go. Right? So then, you know, when they invented this strong force, then the next thing you know is they can't reconcile the strong force with gravity. They can't put the two together. Right? So now they have this big dilemma, and now they keep adding dimensions to try to make it work. You know? It ain't gonna work because the strong force does not exist. It's a figment of our imagination. It's gravity acting at the atomic level. You're dealing with mini black holes. That's why the electron spins at near the speed of light. Right? So, if you take 2 of these protons, little black hole protons, and you calculate their strength, I'm going to spare you the equations. Although you could easily follow them because they're simple. The force between 2 black hole protons is very large, so it can overcome the repulsion. But then you calculate how fast 2 protons like that with that force would rotate around each other. And you find that you know, they rotate at very high speed, 10 to the 32 centimeters per second square, very rapidly. And then you calculate, that was their acceleration. You calculate their velocity, and V turns out to equal 2.9 multiplied by 10 to the 10 centimeters per second. Anybody recognize that number? Very good. The speed of light. V equals C. So now, these little protons at the center of the atom are not only infinitely dense, but they're spinning at near the speed of light. They're spinning at very high velocity, near the speed of light. So you know all these masters that walked around saying, you are light? They meant it. Can you like visualize yourself? Can you sense yourself? Can you sense your atoms as mini black holes spinning near the speed of light? This is how dynamic you are. This is how energetic you are. It's an amazing thing. You're transferring information to the universe and back at the speed of light. You're flickering really, really quickly. Push the vacuum, to the vacuum, back out, to the vacuum, back out, to the vacuum, back out. So who are you when you're the vacuum? Have you explored your vacuum self? You know, please don't talk to your shrink about this because it might put you some nasty drugs, you know. Half the time I'm the vacuum. I don't think they have any drugs to stop that one. So, you know, I can skip some of that, but I just wanted to say, you know, you're flickering, you're informing the vacuum, flickering in and out of it very, very quickly. Everywhere is happening like this. It's really a remarkable thing, and it's really important to become aware of this interaction. And when it's happening, you start to realize that maybe linear motion is not quite what we think it is. And what I mean by that is that if we live in a fractal universe of infinite division, from infinitely big to infinitely small, then movement from point A to point B is quite different than what we assume it is. Okay? You can start to look at your hand and say, okay, my hand is going from point A to point B. And I'm going to calculate how fast it did that. Well, you know, if you close the box around your hand, then you can do it. But if you realize that it's all embedded to infinity, then you'd say, well, while my hand was going from A to B, the Earth was rotating. So I got to add that speed. And then while that was happening, the Earth was rotating, then the Sun, it was rotating around the Sun. So I got to add that speed. And then as it rotated around the Sun was moving through the galaxy. So I got to add that speed. So you know, your hand is now moving at millions of miles per second, you know. And then like, you know, you keep adding because this galaxy is in a supercluster, which is in a in a cluster, which is in a supercluster, and so on. In a universe, in a multiverse, next thing you know, your hand's going at the speed of light. So how do you define movement? You realize that your hand is not moving linearly from A to B. Your hand is appearing, disappearing, appearing, disappearing, undoing itself, redoing itself, undoing itself, redoing itself, every time going to infinity and back. Being informed of where it must reappear. Just like a movie, where there's a bunch of frames, but if you move the frames fast enough, they appear to be smooth. And if you realize that, you're interacting with the vacuum this way, and you're good at manipulating the vacuum, what I call vacuum engineers, masters, you might be able to get your hand to disappear here and reappear over there, and skip all the points in between. This understanding, this technology, this capacity to interact with the vacuum, both in your own being, but very specifically in laboratory, leads to technology that will blow your mind. Leads to technology that not only brings us to a capacity of abundance of energy, infinite amount of energy, space drive and so on, but to actually transfer the information from one end of the galaxy to the other end of the galaxy without having to go through all the points in between. And I assure you, although that might sound like far in the future, all this is just around the corner. and I knew there was this big problem in physics. It's a problem that's part of the vacuum catastrophe. That's a 122 orders of magnitude problem. And that's because, remember I was saying that that the universe has this dark energy in it that's inflating the universe. The vacuum has this energy in it at the cosmological level. When the physicists calculated the density of that energy at the cosmological level, they found that it was 10 to the minus 29 grams per centimeter cube. All right? So it's a really, really teeny amount of energy per 30 minutes. Okay. And at the quantum level, it's 10 to the 93. So it's a huge difference. If the vacuum has 10 to the 93 grams per centimeter cube at the quantum level, how is it that we're measuring 10 to the minus 29 grams at the cosmological level? And this 122 orders of magnitude different. That's huge. That is currently the largest problem in physics ever encountered. It's commonly referred as the worst prediction physics has ever done. And I realized, wait, I've got a 10 to the 55th gram proton that is a result of the 10 to the 93 grams per centimeter cube density of the vacuum, okay? And so per proton volume, right? And what happens if I grow that thing to the size of the universe? Obviously, the density is going to drop. So I grew it to the size of the universe, and my result was 10 to the 30th gram, minus 30th gram per centimeter cube, really close to the measured cosmological constant. So I was like, wow, it actually works. And you know, in physics, this would be close enough that you could say, well, I'm going to adjust the size of the universe till I get the right number for the measured value. And that's going to give me a prediction for the size of the universe, right? Which we don't know. There's a wobble between, it's between 10 to the minus, 10 to the 27 to 10 to the 29. So 10 to the 28 is usually the value that's given. But it's rough, obviously, because it's cosmological. So I said, well, how can I get a real number? Because I could have adjusted it, but I didn't want to cherry pick. So I said, okay, well, I know the mass of the universe, since this should be accurate. If it's accurate, if I do the Schwarzschild condition of that mass, right? Remember that equation? If I solve that equation, it'll give me a radius for the black hole universe. Let's see if I do the same thing with that radius. This would be the first time we get an exact radius for the universe. So I did that, and when I grew it, boom, 10 to the minus 29 grams per centimeter cube. I was like, okay, this works. This works. And again, if this is correct, this is the first time we know the exact mass and the exact size of our universe. So I said, wow, you know, this is showing so much evidence of the holographic principle of this concept that from studying the proton, I can actually understand the whole universe. I should look at the holographic principle and apply it. The holographic principle in physics is utilized to describe the entropy of black holes. That would be the amount of thermodynamics that come off a black hole. You could think of it in Kelvin. And what is currently used is that they map little Planck's distance on the surface event horizon of the black hole and then count them and make this calculation and they get the entropy of a black hole. I started to think this way. I started to apply that. So I said, okay, it's holographic. Let's look at relationship. I took the Planck's distance I knew was I made it a surface, and I plastered it over the surface of the event horizon of the black hole proton. But when I plastered it, I took the surface area of the proton, right? And I divided it by the number, by the area of the Planck's distance little circle. So it has to be space filling. That means the circles cannot be one beside each other like that, because if they were, there would be little spaces in between. It has to be space filling. You guys follow me? So when I said, well, how could they be space filling? Well, guess what I got? The flower of life symbol. And I thought, wow, you know, if it comes out, I'm gonna shit my pants. I almost did. I almost did. Because what I did is I said, okay, how many of those is there? Those are all little Planck's oscillations, right? And there's 10 to the 40th of them. So there's a lot. And I said, okay, out of those, remember in the middle is all the little Planck spheres, right? See, these are little Planck spheres in the middle in 3D that are projecting onto the surface. That is the holographic principle. You guys saw that? Do it again. Okay. That's actually the beginning of the movie Black Hole that Guyam just released about the research I'm doing. So let me try to, oh, I missed it. Let me do it again, just so it's clear. So inside the volume of the little proton, right, is all the Planck spheres, right? That's how I got the 10 to the 55th, right? So this are all the little Planck spheres. Here you see tetrahedrons because they tiled. If they produce the flower of life structure, they tiled just like tetrahedron structures. And that's where the work I'm doing links with the work that Richard Hoagland is doing and others in hyperdimensional physics, because that is the structure of the vacuum, right? And so I said, okay, these spheres are projecting the information of the whole universe onto the surface. So so it's a projection onto the surface, which is the holographic principle. And then we're going to see why the surface has less than the interior in a minute. But you see here, it's projecting onto the surface. That's what I was trying to show here. Okay? And it's a curved surface. It's the surface of the event horizon. So when I did that, then it's slow for most people. I'm going to write here. So what I did is I took the number of little circles on the surface, right? All the circles on the surface. That's 10 to the 40th. Can everybody see this? 10 to the 40th. And then the number inside is 10 to the 55th, right? It's the mass of the universe. Basically, divide the number of little Planck surfaces by the mass of the universe. Okay? And what I got was exactly, what I got was exactly R sub S, the Schwarzschild mass. 10 to the 14. 10 to the 14, which is the Schwarzschild equation. I have the Schwarzschild equation here. Gravity outputted completely geometrically. No curvature of space-time, no geodesics, just pixelation of the structure of the vacuum itself. This is quantum gravity that I've been looking for all these years. And the solution is exact, okay? Exact only if the tessellation is space filling, the flower of life. Under the paw of the foo dogs is a sphere with the flower of life tessellated over the surface. The guardian of the knowledge. Then I said, okay, if this is really cool, if this is true, I should be able to continue to do relationship in there and get all sorts of information about our universe. So I took the number of Planck's surfaces, 10 to the 40th, but this time I divided it by 10 to the minus 39, which is the volume, proton volume. The volume of the proton itself, instead of the number of Plancks in there. And the result was 10 to the 79. And when 10 to the 79 came out, I recognized it right away. I said, oh, this is really close to the estimated amount of particles in the universe. Right? We know there's approximately between 10 to the 78 to 10 to the 80th or 10 to the 81 amount of particles in the universe. And so, if this is true, this would be the first time we have an exact number for the actual amount of particles, right? Well, you can think of like protons, right? Most of the universe is hydrogen atom with one proton, so in general, just protons are counted in our universe. So just you could think of the amount of atoms in the universe, if you'd like. So I thought, well, this would be cool if this is exact. So then I did something a little weird. But, I have those moments. I did something a little weird that I'm going to show you I rectified right after, but it gave me the right answer anyway. But I said, okay, each one of these little circles is like a little micro wormhole connecting all the protons, all the Planck's length in the universe with all the other protons. The reason why I thought that way is because that discrepancy between the standard mass and the Schwarzschild mass, I kept on seeing in my head and in my work, in my philosophy, that it's because you can't just look at the mass of one proton because it's influenced by all the other protons in the universe, right? Remember, it's not isolated. So if it's linked, okay, I said, okay, then I got to divide the Schwarzschild condition by all the other protons to see what would be the influence of a proton on one little Planck's distance. So that's what I did. I divided the number of Planck's distances, right, by the number, I divided the mass, the Schwarzschild mass, by the number of protons in the universe I was getting. And that gives me the standard mass of the proton, meaning when I divided the two, it gave me 10 to the minus 69, which would be the 10 to the minus 65. So that would be the influence of one universal proton, another proton, on one little Planck distance. You all following me? Connected through that one wormhole, right? so that every internal structure of every proton in the universe is all one thing connected through these wormholes, right? So I was looking for the influence of one point of contact, one wormhole. And that gave me 10 to the minus 65. And then I said, okay, let's multiply all those together, all the little wormholes together, the influence of all the other protons, because we're looking at the proton from the outside. And the result is when I multiplied the two, I got the exact mass of the proton, the standard mass of the proton. 10 to the minus 24. I was blown away. I was blown away because it was extremely exact. I mean, it's 0.019% exact, which is inside the measurement error in laboratory. So this is actually most likely the exact mass of the universe, of the proton. But think about it. I could have skipped that step, since I know the amount of protons in the universe, assuming that this 10 to the 79 is correct. I should be able to just divide it by the mass of the universe. That would tell me how much each proton weighs, right? And when I did, it came out exactly right. This is the mass of the universe extrapolated from the inside of the proton and divided by the number of protons in the universe extrapolated by the surface, and I got exactly the mass of the proton, which was like incredible, because you gotta see what I saw there. You've got a huge number, 10 to the 80th, right? 10 to the 79. And you're dividing by another huge number, the mass of the universe, and you're nailing 10 to the minus 24 grams, teeny weeny proton, exactly right. Unbelievable. Unbelievable. One too many proton in there, and this is off. A little too much mass in the universe, and that number is off. But it gets it right on the button. So this cannot be, random. And now, and I've solved this, and this is actually in a second paper I'm about to publish. I've solved this in a much more classical way now. I've got this equation that's like m equals mc squared type that everybody is going to be able to solve with a calculator, any students in high school. Anyway, it's super simple. It's a clear relationship, and that's going to come out soon. Thank you. Thank you. But even more important is that this ancient symbol that's found all around the world, that was so important to so many ancient civilizations that they made sure that it would survive all spans of time to reach us today, seems to be the exact solution to the holographic universe, giving us the exact correct answers, and that is remarkable. As well, that leads to a deeper understanding on how we would build technology to reproduce those dynamics in laboratory so that we can access this energy. Now we understand quantum gravity. We understand that gravity is basically just a ratio of information to surface area. And that actually this surface area interaction, you see, this 10 to the 40th little Planck's termination of wormholes on the surface but there's 10 to the 80th particles. So how is it that 1 is connected to 10 to the 80th if it's only got 10 to the 40th possible connection? Well, that's because when you, it's not only holographic, but it's fractal in nature. That is, one little proton is connected to 10 to the 40th particles, and these 10 to the 40th particles are connected to 10 to the 40th particles, and so on. So that you have this fractal progression, you know, that you can identify. And this is actually why I called my theory 25 years ago the holofractal graphic theory. Is because it's holographic and fractal in nature. And I knew it was in there somewhere, but I finally mathematically solved it. The other thing that's really exciting about this is that this is the yardstick. We can apply that to infinitely big. You know how the Freemason have that, that compass symbol as the symbol of the yardstick of the universe, the geometry of the universe, God's, you know, scale? Well, this is what we've got. Meaning that I can now tell you, from studying the proton, this little teeny bitty thing, the mass of the universe, the cosmological constant, the energy of our universe, the size of it, right? The gravitational field, but not only that, I can tell you how many of our universes there is in a larger one. And what is their energy level? And what's the energy level of that larger universe? And what's its scale? And all sorts of information. And then I can tell you how many of those larger universes there is in a larger one. And again, and again. So now we have the fractal yardstick and the network connection so that we can actually navigate our universe and the multiverse we live in. And I wanted to just say, although all this seems very technical and it seems very, you know, mechanical, maybe, it has so much deeper meaning and deeper implication for our understanding of ourselves, the universe, and the dynamics that connects us all. You can actually go, I mean, when I solved these equations a few months ago, I've been meditating since I'm 11. I've been thinking about this stuff all my life. I got a deeper, new level of the interconnectivity of all the atoms of my body. They all like had these moments where I felt like the wormhole linking to the whole thing. It's like, oh my God. And this is available to you. This sense of connectivity, this experience of connectivity through the structure of the vacuum. Never forget that you are 99.99999% energy of the vacuum, and that is actually informing you every second, and you have access to it. This is why all the masters have asked everyone to spend the time every day, even if it's a few minutes, to turn your senses inward and go to that point. Go to that point of singularity. And connect with the whole, connect with the holographic nature of all the universe, and be the infinite being that you are.
Okay, so now we've got divisions in the vacuum. What dictates those divisions? How is the vacuum structured? If the vacuum is divided in very specific ways, then it must have very specific division structure. Then the vacuum has structure. How can that be? And what would be the structure? I wanted the key to the equation of vacuum division. I wanted the key to the creation of these boundaries. Because if I knew the key, then I could create one of those boundaries. I come upon these pyramids, Chichen Itza, just out of the jungle, these huge pyramids sticking out. And then I start to think, well, wait a minute, I'm looking for a fundamental structure of creation, and there's these buildings, these pyramids, everywhere around the world. And I'm thinking, well, why are they all building pyramids? Why did the Egyptians, the Mayans, the Incas, all these people are building pyramids? What's with pyramids? I'd come to conclusions that the universal forces, the vacuum division, seem to always generate a very fundamental, specific geometry, and that geometry was the geometry of a sphere. It makes spheres, little spheres, and bigger spheres, and then assembles them together and gets all sorts of things. But I was thinking, wait a minute, though. The sphere would be the part that's on the outside. The sphere would be the event horizon. The sphere would be the boundary from which things radiate. What I want to know is what's inside that. I want to know what's the geometry that holds the sphere together. How does the sphere pop out in the vacuum? And it wasn't obvious, but I started to study geometry, and I realized that the sphere is the most unstable geometry. It's got the most surface, and it doesn't have structure, so it's the most unstable geometry. So how would it hold together? And I thought, well, it has to have the most stable structure in the middle. And not only would have to be the most stable structure in the middle, whatever the structure was that was holding the sphere, that was dividing the vacuum, that structure had to be in perfect equilibrium, because it had to be able to be observed as the vacuum. That is, if it had infinite amount of density, at the end of the day, when all the density, all the vectors of the geometry would collide at that level, the geometry that would result would have to be in perfect equilibrium so that we would think that it's empty space. That we would think that it's a vacuum. So all that logic had come through, and so I started to study what would be the smallest, the most stable, the most equilibrium geometry I could find. And what I had found is that the exact opposite of the sphere, which is the largest and most unstable, was the tetrahedron. And if we look at a tetrahedron, it's made out of, it's the smallest volume possible, okay, with equal edges and equal faces. And it's made out of 3 faces on top and 1 on the bottom. So 4 faces generates, it's like a pyramid with a triangle base. And this is actually the most stable, fundamental, and the most fundamental geometric structure we can find in nature or in geometry. So I thought, well, okay, it probably has something to do with the tetrahedron inside a sphere. And I had come to those conclusions. So I didn't know why all these ancient people were building pyramids. And I, went to my local library, and I'm looking around, and this book pops out at me, and it's called Mystery of the Mexican Pyramids by Peter Tompkins. So I pulled out the book, and I opened it randomly, if there is such a thing. And it opened on page 280, I believe. And it had this graphic on it. A tetrahedron inside a sphere. This was the first time I was starting to study ancient texts. And I realized that this graphic came from the result of a 20-year investigation of the plaza and the pyramidal structures that are found north of Mexico City, and it has the moon pyramid, the sun pyramid, and the person that did the survey there did it for the Americano Society is Hugh Hollison Jr., I believe, and he came to very amazing conclusions. First of all, when he started to map the whole city at Teotihuacan, he found that the sun pyramid and the moon pyramid and all the other buildings seems to be in appropriate relationship to each other, so to reproduce a map of the solar system, including Pluto and Neptune, which were planets that we didn't discover in modern age until the early 1900s. We started to find that there was very specific ratio relationship between the buildings and how they were placed and mapped, and he thought there's some kind of fundamental code that's being used here to build all this, and maybe there's some kind of fundamental message. And after 20 years of research, it seems that everything seemed to be pointing out that we should be looking, or that the mathematics that they used had to do with a tetrahedron inside a sphere. But more importantly, at the time, there was a comment that was made in that book that the fundamental equation that Hugh Hollison Jr. used to map this out matched a very specific mathematics of Buckminster-Fuller, which related to an isotropic vector metric. And the isotropic vector metric is made out of 20 tetrahedrons. There's 10 on the bottom, 6 on the second level, 3 on top, and 1 on top. It's actually a 4-frequency isotropic vector metric. This fundamental geometry was part of Bucky's concept that the universe had a mathematical geometric blueprint to it, so something very similar to my thoughts, and that blueprint related to this very specific metric. So I got very excited and I started to study it in detail. I looked at it in different angles, and I started to think, well, okay, so if I'm not dealing with just one tetrahedron, then there must be the interaction of the tetrahedrons may have different geometries involved in it. And since I was really investigating the structure of the vacuum, I was very interested in the negative space between the tetrahedrons. So I eliminated the tetrahedrons from the space and extrapolated what was in the middle of it, in between the tetrahedrons. And what I found is that what's in between the tetrahedrons is octahedrons, right? Now, an octahedron is a double bonded pyramid, okay? Emphasis on the word pyramid. So I was excited. Oh, here's the pyramids. It kind of linked with the ancient concepts. Okay, well, that's interesting. And then as I kind of traced all the vectors of the pyramid and in my drawings and in my head, I didn't have a computer at the time. I realized there was some strange negative cavities inside the isotropic vector metric. So here's our isotropic vector metric, and here's the cavities that I noticed that were inside it. Now, if there's 20, so let's put it this way, and if we look in between, there's our octahedrons, okay? But in red here, we've demarked that actually there is another set of tetrahedrons in the middle that are pointing inward, that are pointing down, right? And that are rotated from the initial metric. When I found those, I was surprised because this is thought to be an isotropic vector metric. I thought that must be the same everywhere. There shouldn't be any asymmetry. And certainly, I was looking for the geometry of the vacuum. So I was certainly looking for something that was in equilibrium and couldn't have asymmetry in it. So I thought, well, there's one thing for sure, is that if the universe is polarized, it cannot be that the geometry of space would have only one polarity of the equation. It would have to have both sides of the equation, and I had to add the reverse metric to it to get the polarity, the male, the female, the plus, the minus, the white, the black, and so on. So I added another metric below it, but when I did so, if I put one metric base to base to the other, if I put another one base to base to this one, then I have another problem. And that is, I don't get a sphere. I get an egg-shaped structure. And I was looking for the sphere. And then eventually, I did push one into the other. And I realized that when they would be in perfect relationship to each other, then I would get a perfect sphere. However, what got me extremely excited is that when I pushed one into the other and rotated so that it would be in perfect polarization to each other, the central red space that I didn't know were for what were exactly in the right position to accept the reverse metric without having me distort the geometry or remove tetrahedrons or anything like that. So that the polarized metric would actually be incomplete without its better half. And that when the second metric was inserted into it, it would take exactly the spot to create perfect symmetry at the center. And I was really excited because I was looking for perfect symmetry equilibrium. So I started to render in my head, what is the geometry of these tetrahedrons coming in the middle? And that's when I realized that the result of the two metric intersecting with each other to create the perfect sphere generated in the middle what is called a cuboctahedron, which is 8 tetrahedron coming together, which was called by Buckminster Fuller the vector equilibrium, the only geometry in which all vectors are in equal proportion to generate perfect equilibrium. I had found the geometry of perfect equilibrium from the polarity of the two isotropic vector metrics coming together. That's the fundamental, basic geometry of equilibrium, but it actually didn't fully work. That is, I still had points on the edge of my metric here, right? I still had vertices on the edge of my metric that had holes in it, right? So there was a symmetry. This middle structure with the two isotropic vector metric was completely filled, but the edge was not. So I had still a symmetry. I still didn't have equilibrium. And I thought, okay, well, my only solution is to continue to add tetrahedrons until I get equilibrium at all levels. So I continued to add tetrahedrons. I covered the spaces that were open on the edge of the metric. So I had to add 3 tetrahedrons to every edge, which was 8. So that generated 24 more tetrahedrons. So remember, there's 20 tetrahedron in one isotropic vector metric. 2 makes it 40, plus 24, added up to 64 tetrahedron grid. And that, when it came to me, at 64, it all came together. Why is that? Because when I put those added 24 tetrahedron, I realized what I had done. I realized that I had generated a vector equilibrium in the middle, but now I had generated a larger fractal vector equilibrium on the edge. And so now I had a metric that was growing from one vector equilibrium to the other, to the other, to the other. And interestingly, they grew in perfect scale, in harmonic scales, or in octaves, if you want. And it was a three-dimensional fractal. This is actually one of the only true three-dimensional fractal I believe exists. And it grew radially, which is what I needed for the radiation part. And then I realized something even more significant, is that the fractal growth could be generated from 8 star tetrahedron. So 1 star tetrahedron is 8 tetrahedrons coming together to make an octahedron in the middle. Everybody sees that? 8 star tetrahedron, 8 stars like that coming together, okay, to create the vector equilibrium. Right? So 8 of these coming together to create the vector equilibrium. And when I realized that, I saw that the star tetrahedron is 8 tetrahedron pointing out, and that the vector equilibrium is 8 pointing in. And now I had both sides of the event horizon, the radiative side and the contractive side, all in one mathematical metric that was producing both to generate the feedback of creation. So I realized this, and it was like the 8 star tetrahedrons coming together to create the vector equilibrium in the middle. Just like this. And when the whole thing was put together, it would generate a vector equilibrium in the middle, right? The vector equilibrium in the middle. And then it would generate the next fractal vector equilibrium on the outside, right? And so it was a radial growth generating scale in the vacuum. I believed I had found a fundamental structure of equilibrium for the vacuum state. Now I had to understand the dynamics that fundamental structure generated in the field equation, the dynamics of it, not the static view of it, but the dynamics of it, the angular momentum, the rotational part of it, the field equation that emerged from it. Because remember, the vacuum state geometry would be the structure that goes towards infinitely small, that collapses into singularity. There's the other side of the equation, the feedback, which is the radiative side, which has all these energy levels and all these dynamics in it, and that had to match to the geometry of space. From this seed, how would the field get generated? I had the static model of the structure of the vacuum, but that was only the vacuum state moving towards infinity. I didn't have the vacuum state generating the electromagnetic radiation from that division of the space. And so I started to, realize that they had to be angular momentum, they had to be spin involved in the space-time manifold to generate that boundary. In order for the vacuum to generate a boundary, it had to have some kind of shearing, and in technical terms, this is called shearing modulus, that would divide the space, that would fracture the structure at very specific intervals. I realized that they had to be gyroscopic reasons. They had to be gyroscopic dynamics of the angular momentum of the metric of space. And I started to study deeper and deeper in physics, and especially in Einstein field equation, how we dealt with rotation and angular momentum. And I realized that in many cases, we in general try to avoid spin and angular momentum. We try to like make things freeze up so that they can get simpler and easier to map out. But when we do that, well, then we most likely lose a very important component. And then I realized that we had done that with something very, very fundamental. And I started to study how Einstein came to his equations and how his equations were solved. So Einstein did this. He basically, in general relativity, he extrapolated that gravity may not be an internal force of an object, but instead the force of that object applied to the structure of space-time itself. And the way you can describe it simply, imagine a surface of a trampoline. And that trampoline has a big ball, a heavy ball on it. Now the surface of the trampoline around the ball is going to curve like this. And that you could call space-time curvature. And if you took another ball and you put it in the trampoline, it would want to rotate or roll or have an orbit around that first ball because of the space-time curvature around it. This is the typical visualization that you get from space-time curvature. When Einstein wrote this idea of this metric, curving and creating this space-time curvature, he didn't solve it. He just threw out the idea, basically. And he published it. There was a German physicist on the Russian front that got a hold of his paper. His name was Karl Schwarzschild. He solved Einstein field equations. And so that was the first solution to Einstein field equation, and it's called the Schwarzschild solution or the Schwarzschild radius. The thing is that when the Schwarzschild radius was solved, when Einstein field equations were solved for the first time, the result of the solution was nothing else than a black hole. Okay? That is, when he tried to solve the solution to calculate how much gravity something produces, you had to have infinite potential in the middle to solve it, meaning it creates a nonlinear infinite potential at the center. His equation predicts black holes. You know, at the time, this was highly theoretical, and nobody had ever thought that they would actually come across a black hole in the universe. So everybody basically ignored that part of the equation. This was very interesting, that the high curvature of the equation was never truly fully acknowledged, because when you approach the center of the equation with the curvature of space-time, the equation of Einstein goes towards infinity. So remember, I was telling you everything is a black hole because it's divisible to infinity. Well, here you have Einstein field equation telling you that it is so. That in fact you need that singularity in the middle in order to even calculate the weak curvature. And basically what we did is we used the weak part and we just let go of the other part unless it was called a black hole. What I'm saying here is that that first approximation had no rotation and predicted black holes. Okay? There was a solution that was given to Einstein field equation after Karl Schwarzschild. It took a very long time. It wasn't given until 1965. In 1965, the Kerr and Newman solution was rendered in which you had a black hole, or the object was allowed to spin and have charge. So it had spin, angular momentum, and charge. And it took all the way from Einstein writing these equations to 1965 before that was able to be figured out. So you can imagine the complexity, and this is basically the solution that's mostly used to interpret what we see around stars, black holes, galaxies, and all this. There's a problem though. When you take these solutions and you apply them, for instance, to a galaxy or to the universal size, the result of the equation does not match observation. Okay? The result of the equation only predicts 4% of what we see out there. All right? That is, in order for the universe to look the way it does, or for a galaxy to look the way it does, with the amount of mass that we are seeing in that galaxy or in the universe, and when we put it in the Einstein field equation, it doesn't match. What they have to do, and what they've done, which I believe is a complete cop-out, is that they've added 96% of the mass that's missing and the energy that's missing. They called it dark matter and dark energy. It's very, very convenient. Instead of revising the equation, they assume that it's something out there that they cannot measure and that they cannot see. So that's very convenient, because who can tell them it's wrong? Right? They've been looking for dark matter and dark energy since then. Now, I think they will detect something. However, I don't think it's going to be what they think it is. I think the error is in the equation. And the error in the equation is describing, if this error would be corrected, would describe something that's out there, but that's not dark matter or dark energy. It's only a force that allows these dynamics to happen. And that force, I realized, had been omitted. And I'm going to show you how I found that out. I studied the Kerr-Newman solution that had finally added rotation into the space-time, so that if an object was rotating, they could calculate that as well. The thing is when they did so, they wanted to get rid of complexity as well. Because angular momentum and gyroscopic effects are so complex, they did something very strange. They decided to eliminate the gyroscopic effects of rotation, like eliminating Coriolis forces and torque and things like precession and all this. Well, how would you do that? Well, the way they did this is that they attached the frame of reference to the rotating metric so that there would be no force. Now, this is a little trick that's used in physics and that really tweaks the result. Now, what they did is this. Imagine this. You've got a shaft that's turning, maybe on the lathe here, right? Or maybe there's a V8 motor spinning this shaft, right? And it's spinning at 5,000 RPM and you're in front of it. And in a moment of illumination or in a moment of extreme stupidity, you grab onto that shaft, all right, with all your might. Well, you're going to experience some effects, okay? Those effects have to do with shearing, like your skin flying off, you know, heating, like smoke coming off your fingers, you know, all sorts of effects like this that are certainly uncomfortable and that have to do with the force of torque applied now to your hands, right? That's forcing that shaft to spin. All the, you know, 300 horsepower of that V8 motor is spinning that shaft. Well, if I grabbed you at the exact moment that that you went to grab that shaft, if I grabbed you on your center of gravity and spinned you at the exact same rate, you would feel no force. You would feel no effects in your hand. It would be stationary relative to you. You see? However, I could still say that I'm accounting for angular momentum because I could count the turns that you're going around. So I would have a frequency rate of angular momentum. You see? And that's what they did. Why did they do this way? It actually goes all the way back to a fundamental assumption that was made, that things are spinning in a frictionless environment forever. That is, the assumption is, because if you ask a physicist, what is making the Earth spin? They'll tell you it's because it's in the solar system that's spinning. Then you say, well, what's making the solar system spin? They say, well, it's in the galaxy that's spinning. Well, what's making that spin? Well, that's in the supercluster. Well, what's making that spin? Well, that all started in the Big Bang. There was the Big Bang, and then all the energy through everything spinning, and it's been spinning in a frictionless environment since then. So we don't have to account for spin because it's inherent to the Big Bang. First of all, that doesn't tell you where the energy came from to generate that moment of impulse, but certainly it's a very, very large generalization because when you look around, we just happen not to be in a frictionless environment. I mean, it's the same thing at the atomic level. They tell you that electrons spin perpetually because of being in a frictionless environment. They got spinning at the Big Bang and they're still spinning now at 99.9 something the speed of light, right? Those electrons. Now that's a lot of spin for a long time. And when you look out there, it just happens that it would be true if there's only one atom in the universe. But as soon as you have two atoms, now you have interacting fields. You have friction, you have collision, you have all sorts of things happening. Gravitational fields acting on each other. Not only that, in order for that statement to be true, then all objects would have to be solid, true and true, homogeneous, which we know they're not. For instance, the layers of the sun rotate at different rates and have huge amount of frictions between them. Think of the inside of the Earth. Is the inside of the Earth spinning in a frictionless environment? I don't think so. It's spinning at a different rate as the surface, obviously because we're getting a magnetic field resulting from a dynamo effect. So what's making the inside dynamo spin against the mantle? You're talking molten lava, not frictionless. Not frictionless at all. Solar winds in our solar system, the gravitational pull of the Earth. You see, here I have two eggs. Here I have a hard-boiled egg. Fairly, you know, constant density through and through. Okay? Here, an unboiled egg. High level of viscosity in the middle. Okay? I'm going to spin the hard-boiled egg on the floor. Now imagine this hard-boiled egg was in a frictionless environment, or a very low friction environment. It could spin, oops, let me try that again. It could spin constantly and homogeneously as it does here and slow down, but That's mostly because of friction on the floor, right? Now, let's imagine that it was frictionless, but you could see how that could be possible. But now, let's try to spin an egg that has high viscosity at its core. It stops very quickly. Most of the angular momentum is absorbed by the viscosity of the central core of the egg. Galaxies are just like a non-boiled egg. It has all sorts of density, plasma density change, all sorts of friction, and all sorts of different levels of viscosity, and so is the center of the Earth. There is actually currently no appropriate geological description on how the moment of inertia of our inner core of the Earth occur. How do we get a magnetic field, and what's spinning that dynamo in the center of the Earth? Did you guys have bicycles when you were kids that had those little dynamo on the wheel that created enough current to put up a light in front so you could see at night? Well, in order to spin the dynamo, you still have to pedal. So there's got to be somebody pedaling. There's got to be something forcing things to spin. The new solution that we wrote detached the frame of reference from the rotating metric so that we have an appropriate description of the physics at hand. And the result is that you have torque and Coriolis forces applied to the system directly from the space-time manifold. So let's go back to the analogy of Einstein field equation of the trampoline curving to generate gravity. So basically Einstein said gravity is the result of space-time curving like the surface of a trampoline. And basically what we say in this paper is that yes, and when space-time curve, it doesn't just curve, but it curls, just like water going down the drain, and that generates spin, angular momentum. And that's the source of the spin of all things. And that is an appropriate way to actually describe physics of angular momentum in the universe. So when we add torque to space-time, the solution gives us a very different picture than a perfect sphere. It generates a torus structure, okay, which is a sphere with two holes in the middle at the north and south pole. And because it has Coriolis forces are the forces that makes water rotate in one direction in the north hemisphere and in the other in the south hemisphere, that makes hurricanes rotate in the opposite direction, that makes plasma dynamics on the sun rotate in the opposite direction. Because Coriolis forces were added to the equation, so what we did is we added a term for torque and the Coriolis forces as a secondary rank tensor on the space-time manifold. The result is a double torus structure, a double torus manifold that has this dynamic, which is viewed here from above as a rotating yin-yang sign, if you'd like. Right. And so that's quite a different picture. And it's quite a different view of the universe, because now space-time is the source for spin, for Coriolis forces, for the magnetic fields, and now we can start to drive the whole equations of creation based on this space-time torque, generating even gravity and electromagnetic radiation. Because you see, now we have a direct balance equation. There's a balance between how much space-time torque, how much force is applied on the system, and how much shearing that generates, and how much radiation the system outputs. So now you have a feedback between the gravitational field and the space-time torque. And that was the dynamics that I was looking for. If we look at the torus, from above, what's in the middle? Space, vacuum. The middle of the donut has a hole. This is where singularity would be in the center of a black hole. So at the center of the space-time manifold, where we would expect the Planck's distance at singularity, we find the vacuum state polarization. This is why the vacuum has polarity and structure, because space-time has angular momentum, is rotating, which generates acts of rotation that generates structure in the space-time manifold. And so we approach the center of the torus, we approach that point towards the Planck's distance, and we went in, we used group theoretical models to look into there and solve that point for subatomic particle. And when we were able to solve all the subatomic particles, okay, for that point, all the particles we observed, subatomic particles for that point, which were now linked in our mathematics to the space-time manifold for Einstein field equation for large objects, when we went to that point, the solution gave us a vector equilibrium. Okay? This is a solution given out of a set of mathematics that had nothing to do with my instinctive and logical thoughts that brought me to believe that this had to be the geometry of the vacuum, the geometry of singularity. Yet the mathematics totally confirmed it. This all came together in a beautiful way that generates a full unified field theory in which the dynamics of space-time is that feedback loop between the gravitational field going in and the electromagnetic field going out, and the center vacuum structure, the singularity, which is the fractal space-time grid that defines that field equation. All put together, you get all the particles of subatomic particles and all the mathematics you need to solve gravitational fields, the electromagnetic field, the strong and weak force. What I'm bringing in is that, wait a minute, by modifying Einstein field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation, he should be able to solve all the way down to the subatomic particle. And he actually got really close, I believe, at one time, because a French mathematician contacted him was giving him solutions to his own equation that incorporated torsion. Torsion is the distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, you know, maybe we could solve Einstein field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque in the first place. And that they never went to. They never added the torque to the space-time manifold. if you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum and everything, but omitting to add to an analysis the V8 engine that's spinning it. Now, when you look in nature, you can see these dynamics. Look at this. This is a galaxy, okay? And galaxies have galactic halos. Can everybody see this? It's like a very fade, big sphere around the galaxy. And when when we look at galaxy, typically we only think of the galactic disk, right? And that's because in the galactic disk, there's the most amount of density because the sphere around a galaxy has a huge surface, so things spread apart, so it's not as easy to see. But there's actually more stars in the galactic halo around galaxies than in the galactic disks. And then here, you can definitely see a huge vortex going into the black hole at the center of the galaxy. We can't see the one below it because, these are very far away and we don't have that great of optics and so on. But we know that in general, there is always, or typically, two huge vortex going into center of black holes. In the case of our galaxy, that vortex is, I believe, 3 on the north pole of our galaxy, if you're looking from our perspective, is 3,000 light years long. 3,000 light years long. This is, at the speed of light, it would take still 3,000 years to get to the end of the vortex. And it's filled with gases and high velocity dynamics and high energy dynamics enough that it's actually visible thousands and thousands of light years away from it. Imagine how much torque you need to produce that. Isn't that an obvious example of water going down the drain? Okay, now you'd say, well, wait a minute, when we see these vortices and we follow the particles, they're spitting out. Okay? Well, okay, if water is going down your drain, air has to move out of the drain for water to come down. That's the exchange. We only see the outside of the event horizon. We only see the radiating part of the event horizon. We don't see the space-time torque going into it to force the system to have angular momentum. And so the result is that we live inside a black hole. That's why it's black out there at night, okay? And what we see inside that black hole are smaller black holes, smaller scale black holes that we're on the outside of. So what do they look like? Radiating stars, radiating objects. Because we're on the outside, we're seeing the plasma Coriolis forces dynamics on the outside of the thing. We see the radiative side, we don't know about the contractive side, and that's why most of our physics is based on the radiation. But there's an exchange between the two, and this is the exchange I'm showing here, and that we calculated. These are very large objects, blazars, quasars. They're all being photographed to have these huge vortices. They're enormous. We see them at all scales. This is a quasar. So here you can see 10 to the 6 light years long is this vortex. That is 1,000,000 light years long. Okay? 1,000,000 light years long vortex at the speed of light, 1,000,000 years to get to the end of it. And these things are spinning at near the speed of light when they arrive at the event horizon of the black hole. So very, very high torque. Big engines out there that are not being calculated. Now this is the different scale. Those are called microquasars. We find those even inside our own galaxy. And in this case, the vortex is only 3 light years long. So now you're starting to see the scalar dynamics, the scale change, the fractal nature of the division of space. From quasars to microquasars to collapsed stars or supernovae, we see the same dynamics, the same vortex. Look at this vortex dynamic on this pulsar, which is the result of a supernova explosion. Have you ever seen articles in a layman physics magazine where it says the death of a star explode into a supernova? Okay. We haven't ever experienced the death of anything. We haven't observed that. We really haven't. All we've observed is things changing state. Okay? For instance, I'm not talking esoterically here. For instance, people have all sorts of debate about if life continues after death or eternal or whatever. You don't need to be esoteric. Just take, what you got and extrapolate from it. You have a few billion atoms. There's a lot of cells. There's 100 trillion cells in a human body. And they're all organized in an organized matter. And then all of a sudden, they disorganize. Okay? However, all these atoms are still spinning. You haven't lost one. Okay? They're still out there. They're still spinning. In fact, you might be made out of the atoms of your neighbor. And your neighbor might be made out of your atoms. And so there's no evidence that things actually stop. Because if there is space-time torque going to singularity in each point, then there is angular momentum at all levels and things continue spinning no matter what. What I'm saying is that the friction that's out there is overcome by the space-time torque. So, and that makes it appear as a frictionless environment. So we don't see death. We just see things changing levels of organization, changing scales. And when we see a star exploding, right, they call it the death of a star. But when they focus on that same area afterwards, what do they see? They see a pulsar. Oh, that's nice. They just changed the name from star to pulsar, so the star is dead and the pulsar is born. Let me give you an example. If you were a camera inside a woman's womb, and this woman was pregnant, you would see life developing in that womb. And after 9 months, you would have probably a pretty good relationship with this life inside the woman's womb. All of a sudden, there's a big earthquake in your world, and waters disappear, and there's an opening that opens in the little black hole at the end of this hip joint, and this being that you had a relationship with disappears through that hole. You would experience death. You would think this being is dead. The person on the other side experienced life. crossing the event horizon. So what I'm saying is that our mathematics and our views have now shown us that actually pulsars and supernovae explosions are the result of stars when space-time is torqued into a certain radius, and it generates material inside, so that the Big Bang is only one of those events that generated the atoms of our universe. That atoms are actually being manufactured at the singularity of black holes. And that's the exchange of those atoms coming out, those vortices, as the space-time torque influence those black holes. And when those particles get out of there, they are stuck in the gravitational field of that black hole and accrete on the surface of the event horizon, as well as other atoms that are created by that black hole as it travels through space. And when it accretes too much material, it becomes unbalanced. There's too much radiation for the contractive torque force at the center of the system. The system slows down too much, and the instability generates an explosion. It blows up. What it does, it releases a layer of material so it can regain stability. And so that's what we see. And then it regains stability, and when it does, guess what? The radius is much shorter. The ballerina has brought her arm in, so the thing spins way fast, like a pulsar. Okay? And then if it's fast enough, then we call it a black hole, and we say, look, the star made a black hole. And what I'm saying is, no, the black hole was always there. What we observe now is the dynamics of that black hole much closer to the event horizon, so we see the X-ray emission and all this stuff that we wouldn't observe before. So do you see how the picture is a little different? Now we start to see the universe as cycles in space. Okay, instead of start, stop, start, stop. And you start to see that maybe, just maybe, that's how our universe was created. An enormous black hole that became unstable and blew out a certain amount of its ergosphere, a certain amount of its plasma, which generated all the rest of the stuff we see today. And that those cycles most likely go on and go on and go on forever. Even the dynamics of the Earth plasma, like the dynamics of the Earth stratosphere and the way hurricanes and weather systems move around the Earth, obeys those conditions. That is, the weather systems go from the North Pole down to the equator and then back up. And from the South Pole up to the equator and then back down. They don't cross over. And so on. So there is those dynamics, those plasma dynamics are seen at all levels. In the sun dynamics, we see the exact same pattern, that double torus pattern, in the dynamics of the plasma around the sun. So, and what we see in these dynamics, we see Coriolis force, and in the center of these vortices, what do we see? We see a black spot. We call it a sunspot. And typically we've been told that sunspots are surface events, and I debated this for 15 years, and finally they're finding out that they're not. They're vortices going towards the middle of the sun. Because what you're seeing in a sunspot is a vortex, Coriolis forces going towards singularity, and that's why they're most commonly matched by another one on the exact opposite side, right, that meets at the center.
I was looking at Jupiter through my telescope, and I started to think of the surface feature of Jupiter and that huge red spot, almost 1.5 times the size of the Earth on Jupiter, that constantly, steadily stays at the same latitude. And I thought, what about that dynamic? What is forcing that huge vortex of
Coriolis dynamics to stay at that latitude all the time. You'd expect that it would dissipate eventually, you'd expect that it would move in latitude, go all over the place, but it doesn't. And I thought, what if that structure on the surface of Jupiter is staying there because of the dynamics of the structure of the vacuum, the tetrahedron inside the sphere dictating that energy event to happen at that particular spot on Jupiter.
Upon his return, Haramein began to investigate. He found that not only did the red spot on Jupiter orbit very close to the magical 19.47 latitude of the tetrahedron inscribed in a sphere, but that many other planets exhibited similar dynamics, had come to conclude that some hyperdimensional tetrahedral dynamics had to be at play in planetary structures. He noted that not only did the red spot on Jupiter exhibit the appropriate geometric latitude, but that many other planetary energy events were consistent with this geometry. The largest volcano in our solar system, Olympus Mons on Mars, is situated near 19.47 north latitude.
So I applied the same geometry to the Earth, and I realized that if you put a tetrahedron inside the Earth so that one point is at the South Pole and the other points are at 19.47 latitude on the surface of the Earth in the North Hemisphere. And I looked around to see what was there, and sure enough, I found the most active volcanoes on Earth, the Hawaiian volcanoes, exactly at that latitude. And then I went along that latitude and I found the city of Titihuacan, north of Mexico City, to be at that latitude as well, which is quite remarkable. As we saw in the presentation, the mathematics of that city were decoded by Hugh Hollison Jr. to describe the dynamics of a sphere with a tetrahedron in it. And so not only does the city have these mathematics in it, but the city itself on the surface of the Earth is at that latitude that demarked the relationship of a tetrahedron and a sphere. Remarkable.
However, Haramein's model predicted a 64 cube octahedron structure as the dynamics of the vacuum, and thus he wondered if they could be even clearer resolutions of the other intermediary angles produced by this more complex geometry. If so, it would give observational evidence that the structure of the vacuum is a result of the more complex array of an octahedron-tetrahedron matrix. Haramein looked at the bands of both Jupiter and Saturn and was amazed to find how closely these bands obey the angle relationship of the 64 tetrahedron grid. Furthermore, the recent data returned by the Cassini probe confirmed the presence of an enormous hexagonal feature on the north pole of Saturn, first imaged almost 27 years ago and still persistent to this day. The hexagonal structure, which is completely unexpected in standard models, not only obeyed the latitude dictated by the 64 tetrahedron grid, but is fundamental to the geometry of the cube octahedron at the center of Haramein's conceptual model and mathematics. Even more compelling is the recent imaging returned by the same probe of the south pole of Saturn, which in this case portrays an enormous vortex that seemed to be absorbing matter in a whirlpool. The South Pole vortex leads to the center of the planet, as would the double torus dynamic resulting from the structure of the vacuum, as Haramein's model would predict. Our local star, the Sun, is no exception to this phenomenon. Hot bands of high-energy plasma and intense sunspot activity are found to stabilize at approximately 19.47 degrees latitude north and south.
So when we look at the dynamic of our galaxy, and based on the equations we wrote
with Einstein field equations with a torque term in it. The manifold of our galaxy is no longer, in terms of geometry of space-time, is no longer a sphere, but it's actually a double torus structure with vortices which are visible. We know there's a huge vortex coming out the center of our galaxy. At the North Pole, we've been able to measure it, the North Pole of the galaxy, if we want to call it that way. And it's a large vortex, 3,000 light years long. And we know that the galaxy looks like a disk. And so those are the dynamics of the double torus, you know, with a torus on top and a torus on the bottom, like a sphere with two vortices and an equatorial disk.
We can see that these dynamics are actually present at all levels, even at the biological level, as I was saying earlier. And even you got here by going through these vectorial array dynamics in the womb of your mothers. I point that out all the time. It's like, you want a proof of the fractal nature of space? Well, have you not noticed? People take that for granted. People come out of other people. It's an amazing thing. They do. I mean, I have pictures of my mom with her grandmother, with her grandmother, and like the cousins and everything, and you can see the fractal link of all the mothers, you know, through space-time. And so when you look at the way it happens, even a woman's womb, well, the first cell divides into two, and then the two into four, and when they do four, they arrange into a tetrahedral array. And then these four divides into two each, making 8, and those 8 arrange in a star tetrahedron array. In all of this, you're starting to see, in any case, that this very fundamental geometry is actually how you emerged into this world. You went through that structure in order to get here, and you went through it through the molecular interactions of water. And if we look at what really generates this placements of molecules or cells, well, there's a strand of code inside the nuclear cell that we call the DNA code. And this DNA code is really, you know, an interesting thing, because if we look at the dynamics of that code, it has that spiral kind of torque field look to it. And assuming that these energy levels for cells are correct, and that we can actually describe the cells as like mini black holes interacting things, we would see that at the nuclei, we would see that at the center of the cell, we would see these spiral-like structures. But, and you know, there is a lot of code in your body for you to be here. The complexity is outrageous. I mean, seriously outrageous. If you take the DNA that's in your body, in each cell, there's approximately 6 feet of DNA. And if you put all these strands of DNA end to end, you could wrap it around the world 5 million times around the world, 4 to 5 million times around the world. That is inside your body right now for you to be able to function, so that all the cells know what everybody else is doing, and everybody is organized, and all the information is moving through, and all this is happening because there's a fundamental codonic interaction of the proteins that permits it. And guess what that code is based on? Well, the codon structure of DNA are based on a 4 to the third relationship, which is 64 codon possibilities of combination. I find it interesting that this, 64 possibility codes that generates the amino acids of DNA and so on, matches what we call the affine connection metrical space that Einstein used to produce his field equation, the space-time manifold. It's called the affine connection, and it has a 64-element metric that generates a component for the space-time manifold structures. So then we have a direct link here between the space-time information, the space-time torque, and the way DNA is. Like DNA is like the transducer from space-time information moving through into the world and gathering information. You're like a probe for space-time looking back at itself from the outside and gathering information about its existence. This is a very exciting kind of view that we're starting to see the relationship between the space-time structure and the biology and how biology moves through things.
We saw that the biology seems to interact with all this information, and it seems to confirm a lot of the information. So we can come at it from different perspectives. And one of the perspectives I was coming at it from is the geometric perspective, obviously. And I was playing with the interaction of the spheres interacting. If you put a sphere around each tetrahedron of vector equilibrium, they will intersect. Or if you put a sphere around each tetrahedron of a star tetrahedron, they will intersect. The intersection pattern looks like this. It looks like petals or lobes. Interestingly, the lobes, vertices match the vertices of the octahedron cavity inside the metric. That is, they don't fall at weird angles or anything. They just fall directly at the vertices of the geometry. So now you have curved space interacting with linear geometric space. And I start to ask myself these questions, like, what are these lobe-type structures? And I was reading a lot of physics about waveforms and so on. And it was really intriguing, but it was giving me a lot of headaches. And I was getting headaches because when you look at those things, waves, they typically are represented as a sine wave, right? Something in this fashion. And we are given in general that this is the wave frequency, the wave amplitude, and the wavelength. And that's basically the parameters we describe in wave dynamics. And I was getting a headache. And I couldn't figure it out. I was not able to visualize these waves. I was trying to visualize my view of the universe and to see how the wave dynamics kind of fall into it. How does that all interact and where it all fits in? And I didn't quite understand what a wave was. And so I was trying to read up on it, and I was getting more and more confused. And eventually I just said, okay, I got to kind of go back to the basics. And so I drove my van up to Alpine Lake in Canada, where, you have those turquoise Alpine Lake inside inside a mountains range, so it's very calm. And I grabbed a bunch of pebbles, and I was sitting on a branch on the side of the lake, throwing pebbles in the lake, going, okay, how are these waves working, And I'm looking at these rings coming off the surface and all this. And
it's kind of a simple approach, but I was kind of visualizing it. And I could see that if I took the waveform on the surface of the water and I sheared them, or if I divided them, I could see that it would generate this pattern, this waveform. But I thought, well, this is kind of an artificial way of looking at it because, well, the rock is sinking. It hits the surface tension of the water, and then it pushes the molecules out, and then this wave comes out. And I thought, well, you have to account that the rock has to sink in order for the wave to happen. So how do I account for that? And I was getting confused, and I couldn't understand it all together. And then I thought, but wait a minute, and I thought, if the rock is sinking and the wave is being produced, then it's like more like a vortex. And when I thought of that, it hit me. Oh, wait a minute. I'm thinking in 2 dimensions. You see how that flat 2-dimensional planes get you? That Euclidean flat space? Well, in this way, we think of waves as like, traces on an oscilloscope or something like that. But actually, a wave is a 3-dimensional vortex. I realized, oh my God, if this was in 3D, this would be a vortex along an axis of rotation. And it hit me, oh my God, waves are 3D things. We live in a 3D world. It's not a flat thing. Flatness does not exist. There's no such thing. That's a concept of man, not a fundamental structure of nature. Euclidean flat space are irrelevant to nature. And so I totally got it, and I thought, oh yeah. So, when you think of I looked at the sun and I thought, oh my God, I don't know how many times I thought of a waveform leaving the sun and coming towards me doing this up and down thing. And it's like, not anything in the universe does up and down. It rotates, it spins. And so a waveform coming off the sun is a vortex that's touching me, that's hitting my eyes, that so on. And I realized that this was fundamental. That we commonly, because, and if you ask a physicist, he'll tell you, oh yeah, it's a 3D vortex, but we don't think of it that way. I mean, if he's well educated, he'll know that. No. And we don't think of it this way because it's too complex. We flatten it up so that well, okay, but if you flatten it up, now you don't have angular momentum. You don't have the spin dynamics of the geometry of space, that generate the vortex in the first place. So I was like, oh, okay. So I'm thinking about all this. I laid back on the side of the lake and I was looking at the sun setting behind the mountain tops, which happens quite early in Canada. And then I noticed that, well, actually late in the summer, but I noticed that the sun was going behind the mountains, and the thought came to my head, isn't it cool how we always think the sun is going behind, but actually it's the earth that's rotating? And when I thought that, something hit me. Another thing hit me. I realized, well, these waveforms, dynamics, have to do as well with motion in space. Things move not in this up and down motion. And then I thought, wait a minute. And I thought of the solar system, and it hit me. Typically, and if you have children, please, if they go to school, they're all going to get told that the solar system looks something like this. Let me try to erase this. Okay, that the solar system looks something like this. That the sun is in the middle, and the solar system, and in my school, we even had a little machine with a little thing, a little crank you spun, and the earth went around the sun with the moon and everything. And So they tell you, oh yeah, that's the sun, and then the planets go around like this in an elliptical course, and depending on the interaction of all the planets, it's either elongated or more round. Or you got all the planets like this in the solar system. Well, actually, that is absolutely incorrect. Okay? The thinking of the solar system in this matter is equivalent to thinking that the Earth is flat. The solar system does not behave that way at all. In fact, the solar system it behaves in a completely different way, since the sun is moving through space and the planets are flying around the sun, generating these huge vortices as it follows the equator of the sun. That is a completely different picture. All right? It goes from flat to spacious, to movement through space. And that makes a big difference. All of a sudden, you start to see that even planetary motions, solar motions around the galaxy, galactic motions, supercluster motions, and so on, all have this elliptical, vorticular dynamics of space. They all have this torque dynamic through space. And if you look at the Earth on this vortex, you could say that this is 2000, 2000 for instance, and this would be then 2001, and then this would be 2002, and this would be, this is extremely long distance apart. Millions and millions and millions and millions of miles apart. There's nothing in there, the planets do not come back onto their path. They don't. If they did, we most likely would have the same set of information over and over and over, like a broken record. Okay? And we'd probably get real bored. It would be like Groundhog Year, And so, what makes, and so it hit me in my head, oh my God, what makes every second, every billionth of a second different from the other, every part of the division of space-time different from the other, and why is information changing, is because we are never moving back onto the same coordinates of space-time. We're moving through space-time, gathering information through the system and feeding it back and modifying the structure of space as we move through it. So it was really an important realization. It had implication in the physics I was writing, but as well it had implications in psychology theories and stuff that I was interested in, because you could, I've experienced and experimented on this since then, where if I give this visualization to somebody and I ask them in their mind's eye to move the Earth back along that vortex to an instance, to something that happened in their life that was traumatic, I'm able to get these people to go back to that moment in much more vivid and much more powerful way. And then what I ask them to do is to change their visualization of that experience from their perspective to the 180-degree perspective, like to the perspective of the person that assaulted them or whatever. And then they get a new set of information. And what I believe happens is that new set of information is encoded in that place in space-time. And so all of the rest of the information is changed from there on. And that is actually the effect of psychology, asking you to go back to an instance. But if you don't know, and I think that's where psychology could get some help from this theory, is that if you don't know the true dynamics, the fundamental mechanics of that motion through space, you're going to try to visualize it in something that's going back in time on the same record, broken record, so you can't get there, right? But here, I've had instances where people were able to do that and solve some very, very important issues immediately. And what happens is that if they're there in present time, then all the geometry that catch up with them now opens a whole new sets of geometry for them in the future. What we see is the electromagnetic field coming out as space-time torque radiating after it has been contracted into the system and forced angular momentum. And so that the feedback is continuous. And those lobe structures that are generated when the string goes into stable harmonics resemble very much the lobe structures that I was getting when the spheres are intersecting in this geometry. So I continued to explore these dynamics. I think it was the first supernova ever to be photographed. Is supernova 1987A, and this picture was taken just as the action occurred, and it stunned astrophysicists all around the world that when you expect an explosion of a star, you don't expect highly structured field to be generated like that. So it created a lot of stir in the physics community. And I got really excited because I'm like, wow, they took a picture of the geometry of space, my God. And I thought there was enough energy there that the plasma dynamics actually illuminated the dynamics of space that were going on. And I called my local astronomer, and he just told me I was nuts. And basically, he told me, oh, well, it was just a fluke. It's not going to happen again. Then a few years later, this one was taken. It's called the Hourglass Nebula, and sure enough, it did happen again. And now they've made recently they've made new models of how this could happen. Why is this happening? And they found out that it actually in 3D. This is actually a double torus. It's like two toruses, and the reason is that the star blows off the top and the bottom. It follows the vortices. It's the easiest point of exit, and all the matter goes out and then goes out this way, and it expands a double torus, but viewed from various angles, it looks like so. And so that's very confirming. When you solve Einstein field equations with the torque, people could say, well, okay, but you're adding torque, but what's creating the torque? And the answer for that is that those equations are based on Laplace-Poisson earlier equation, which are equations of density. And what that means is that the density of the field is what drives the space-time torque. That is, because there's different vacuum density from infinitely dense to infinitely undense, but never absolute vacuum, then just like high pressure, low pressures of gases in our atmosphere generates a hurricane, then you get a galaxy, or you get a star, or you get a planet, or so on, because there's density change that drives the whole system. From infinitely dense to vacuum state, in the extremely large. Here you get a hurricane, right? This is off the coast of Florida, and here you get a galaxy. Completely different scales, same dynamics. What do you find in the center of a hurricane? The eye of the hurricane, which is stillness, which is the vacuum state geometry, which is the place where it gets the coldest. And then at the center of the galaxy, you find the black hole, where past the event horizon, all thermodynamics are absorbed and so on, and you leave behind vacuum state geometry. So same dynamics at completely different scale should tell you something about that force and about these change of density. Imagine the change of density between galaxies, which in fact only brings molecules centimeters apart. And then the density inside a galaxy, which is much higher. And then the density inside the solar system, which is much higher. And then the density on the surface of the sun, which is much higher. And then again and again and again, because things are not homogeneous. They have different viscosities and different densities, which drives the space-time torque. This is a picture that was taken at the Sydney University of the energy levels, the energy dynamics around carbon atoms, molecules. And so here we see the same vorticular, dynamics of the space-time torque, according to my views. And we'll get into very high scales level. This is surveys that were done of superclusters of galaxies that's extremely large. And when they looked that far, they expected that things would be quite chaotic and not organized and so on. And instead, they found the exact contrary. These very large scale structure organizes in octahedrons and tetrahedrons array way out there. And these papers are actually published in literature and called fractal or egg carton universe and stuff like that. That's what they're seeing out there. And basically, it's just like this. If you got your nose in the rug, if you got your nose in a Persian rug, there's no way you're going to think that there's a pattern to it. You're just going to think it's all chaotic. But if you get far enough from it, if you change your scale relationship, all of a sudden you start to see the pattern appear. And that is what I believe we're starting to see is the actual structure of space-time and how it organizes matter. Even the table of elements. That was extremely large. Now we're going to much smaller atomic structures. Even the table of elements has been solved by Dr. Moon at the Chicago University to be able to solve for all the protons, neutrons interaction using the 5 Platonic solids, very specific geometry, and then even all of the electron interactions using the Academian solids and the vector equilibrium and so on. This is Dr. Moon, the late Dr. Moon. Well, that's one of the statements he did at the end of his life. We are entitled to seek a geometry of space, or in other words, we are no longer able to talk about empty space. That is, from his findings, he figured that there's got to be some geometry in space that's dictating those particle interactions. If you go even smaller, you're getting to the electron clouds and the orbitals, you find that these probability orbitals match very specific geometries that have to do with tetrahedron and octahedrons. The group theoretical models that predict subatomic particles are based on geometry. I mean, they emerged from crystallography. That's where these models came from, except that typically physicists ignore the geometry. They say, no, that's just a way to solve the equation. I believe that the equation is solvable in geometry because the geometry is fundamental to these particles' interaction. You have to have that geometry to be able to solve it. And, we find that these interacting, group theoretical models match the isotropic vector metric, the vector equilibrium, and so on. So now we're at the extremely, extremely small. Well, how does this come to this geometric structure? Well, if you study the Egyptians, the Mayans, the Incas, all these people, the Indians, all these people, they all did this crazy geometry thing. And they talked about it in various ways. But what is most impressive is that they left very tangible things out there that had to do with geometry. And the things they left out there, if they were little models, 3 feet high with, easy to build, you'd say, well, they must have instinctively figured this out, right? But if they leave behind something like this, it brings a whole new set of questions to the forefront. And that is, how were they able to pull this off? I know that you've heard a lot of stories from your schooling about how pyramids were built. And I know that they told you mostly that these pyramids were built in a very specific way, and that's a fact. That is, between, depending on the theory, 20,000 to 100,000 slaves or farmers that during the Nile flooding every year would go and build pyramids. And they built them, in, depending on the theories, between 20 and 40 years, period. And all this. And that's all nice and dandy. And you have to realize that they teach this as fact. For instance, when you read in those books, it says, well, the pyramids were built by, not may have built by, nothing like that. It's like facts. And you think, well, that must be it, right? But when you think about it, those people that are writing these facts are not engineers. They're not physicists. They don't necessarily understand what it takes to build things. They don't necessarily understand how difficult it is to get great precision from building with stones. They don't necessarily understand that copper doesn't cut stone, and that so far copper hasn't been found to be able to be hardened to cut stone, and so on. So they just throw this stuff out there, and because they have PhDs and they're in the 1800s and they can't imagine of anything else, then everybody goes with that. And I assure you, if you're doing a PhD in Egyptology or in antiquity, in ancient civilization studies or so on, and you write a thesis that these were built in any other way, you're probably not going to get your PhD. And so I was really kind of stunned because I started to study it, because to me, I had solved a lot of these issues, but there was something that just kept on nagging at me. It's like, maybe the history of the earth, maybe the history of our civilization is quite different than what we think it is. And if that's true, I want to know why. Because then I could modify my view of evolution to match the true reality of what happened out there. And that could change a lot of things in the way I think of myself and my ancestors and the way things have been done and my place in the universe. So I started to study these things, and I tell you, when you start studying these things, just a little, and I'm in contact with a lot of physicists, so if I can't run the math, I can ask people their opinion and so on. And when you study these things just a little, right away, you're confronted with amazing, amazing data. For instance, the Grand Pyramid at Giza is 481 feet tall. It's built out of 2,300,000 stones in average, approximately. And the base of the pyramid is 13 acres square. Okay? When they place the last stones on the top of the Grand Pyramid of Giza, which we don't have at this point. You see, the stone on the Grand Pyramid of Giza were ripped out. See, there was a covering on the stones all over the pyramid that was mined to build Cairo in the early 1900s and late 1800s. And so these stones were extremely perfect. The pyramids was much more perfect before.
But still to this day, when you look at the immensity of the building and then you get satellite mapping of the apex of the pyramid, the apex is 1/4 of an inch off the center of a 13-acre square base. I don't know if we have builders in the crew here today, but I guarantee you this type of achievement, after having placed 2,300,000 stone, is not anything any engineering firm with all of the money in the world and the technology we have is able to reproduce today. I assure you. We cannot do that. We cannot reproduce that. You have to divide 1/4 of an inch by 2,300,000 stones to be able to get the accuracy of the placements of the stones. It's a very amazing thing. And then by the time they were done, the orientation of the pyramid to the stellar pole and so on, the way the pyramid is oriented and so on, is extremely accurate, more accurate than many of our current buildings, including telescopes and such. The size, the enormous size of the building is beyond any comprehension. And there's another issue that's very, very dramatic. There is blocks in the Grand Pyramid, in the King's Chamber. There's 100 blocks of granite that have been hoisted to up to 130 feet of elevation in the Grand Pyramid and placed in perfect accuracy to create a relief of the pressure of the stones above with very amazing engineering, so that the whole thing holds together in a way that that is unmatchable with all of our technology today. There's another problem, okay, in archaeology here. Archaeology is really the art of decoding text, decoding the remains of a civilization, and from these decoding, extrapolating their morses, their behavior, their day-to-day life, and so on. Well, if you follow that path, you would expect that somewhere in Egypt, after having placed thousands and thousands and thousands of hieroglyphs in all the temples and tombs and everywhere, okay, telling us everything about the behaviors of their morses, like what they ate, how they went to the washroom, what they did, and how they did it, and everything. I mean, they tell us everything, how they made love and everything, right? That somewhere somebody would have mentioned, oh, by the way, we built the pyramids too. Don't you think? I mean, you'd expect that, right? But not one wall says that. Nothing in Egypt says we built the pyramids. Nothing in Mayan country says we built the pyramids. Nothing in Inca tradition says we built the pyramid. You know how they tell you that the pyramids were built as tombs. And these tombs were there to have the Pharaoh be buried into, right? You've all heard that. And you would expect that the reason they're telling you that is that they found mummies of pharaohs in pyramids. And typically when you look at the books or when you look at the reports from Egypt and so on, they typically show the pharaoh's tombs and then cut to the pyramids and show this all together in a way that you think that you're looking at this pharaoh tomb and it's in a pyramid. Well, it's a fact, however,
that not one mummy was ever found in a pyramid. Not only in Egypt, but anywhere else in the world for that matter. Okay? In Egypt particularly, mummies were all found in underground vaults that have nothing to do with the pyramids. So when you think that a pharaoh that built this huge monument to have himself buried in it would at least put on the front, a little epitaph, so and so from this year to this year, we built this pyramid to bury myself, whatever. There is pyramids in Egypt that were completely sealed when they were found, including the Grand Pyramid at Giza. And the archaeologists, at the time almost treasure hunters, had to dynamite their way in many of these pyramids. They couldn't find an entrance. The entrances were plugged with immense 20-ton boulders that was so well matched to the rest of the pyramid, they couldn't find an entrance. So they would dynamite their way in, and in the case of the Grand Pyramid, they fell into a tunnel, and then they backtracked to the entrance, and then they could clear the plugs. And then typically, in some of these pyramids, they would get to the sarcophagus, and the sarcophagus would still be sealed. And it would have a slab of granite on top of it that weighed in excess of 20 tons. And they would lift the slab with great difficulties, unseal the supposed tomb, and find it empty, completely empty. What was their conclusion? Tomb robbers got there before them. The tomb robbers somehow found the entrance, removed the plug, went in there, took all the treasures, removed the mummy body, lifted the lid, removed the body, took all the rest of the stuff, cleaned everything up, put the lid back on, sealed it back up, went back out, closed the plug, redid everything good, and walked out of there. I don't think so. And so there is huge difficulties in this. There is huge difficulties in these theories. Those are theories. They're not facts. And when you examine these theories, they have immense holes in them. Very large holes that involves thousands of tons of material. So for instance, you have things like the Sphinx. The Sphinx is right in front of the pyramids at Giza. The Sphinx, unlike a lot of people think, is not actually a built model, but is actually a carved statue, carved right out of the Giza Plateau. And there's very interesting things. Now, if you were commissioned to build the Sphinx, what would you do? Now, you've got this huge plateau with this, very good rock in it to carve, and you would want to start carving. So you have to cut the enclosure around the Sphinx body to be able to carve the body. And what they did here is that instead of moving out of the enclosures, little blocks that you would see here, you see, out of the enclosure, if it was you that was commissioned, you'd probably remove 100-pound block, maybe 200-pound block, maybe 500-pound. If you have a good crane, maybe up to 500, 1,000-pound, maybe 2,000-pound. You wouldn't. I mean, why would you try to remove anything bigger, right? It'd be easier to deal with. You move things that match your level of technology. You don't move things that makes it difficult for you to move them, right? Well, the Egyptian somehow, supposedly, moved
these blocks from the enclosure. Now, these blocks are known to have come out of the enclosure because the stratas on the blocks match exactly where the strata is here, and you can actually tell where each block goes. And these blocks weigh in the excess of 200 tons. Now, these guys, seemingly 4,000 years ago, was moving 200-ton blocks casually, and not only just moving them, but stacking them, okay, to create what is known as the Valley Temple or the Sphinx Temple in front of the Sphinx. Those are very, very disturbing pieces of data. They are not simply and easily dealt with or, pushed under the carpet. The Sphinx as well has all sorts of erosions on it that do have impact on our concepts of when the Sphinx was built or carved. New evidence has shown that the erosion that you find on the Sphinx body and then on the Sphinx enclosure, this is the enclosure from where the 200-ton blocks were relieved. The erosion that's seen here demands that there was large amount of rain for long periods of time to create it. We know historically and geologically that the amount of rain needed to create that type of erosion could only happen up to 10,000 years ago after the last ice age. That would mean that the Sphinx was not carved 4,000 years ago, but maybe up to 10,000 to 12,000 years ago. So now you have an even larger archaeological problem. You've got people 10,000 years ago going around with 200-ton blocks. It's a serious issue at that point. There is another temple that's a very important temple in Egypt that's not so well known and recognized, that is very well guarded at this time, that is an anomaly in Egyptian buildings. This is called the Osiris Temple. This is fresh from Abydos. And these blocks are polished pink granite in excess of 100-ton to 200-ton blocks stacked and organized into this incredible building. Now, look at the size of this block above his head. There are tongues and grooves. It's very highly engineered. You got to realize that we're talking about Egyptian here that's supposed to not have the wheel. They don't have the pulley. They don't have a crane to grab things and put them on top of things. Certainly not things that big. And this temple is typically as well a big controversy because, as you see, there's water on the bottom of it. It typically floods annually or almost all the time because it's below the Nile level. The temple is dug into the ground. So when the archaeologists first found it, they said, oh, the Egyptian dug and then built from there. But there's no other evidence in Egypt that the Egyptian would do that to build the temple. And when geologists look at the sides of the temple, they notice that the geological layering on the side of the temple would make it so that it's actually the other way around. The temple was there, and then the sedimentation from the Nile generated all the layers that eventually buried the temple. And then the archaeologists, lady archaeologists, found it and dug it out. Now, that would make
this temple, much older than previously believed, like right now is being dated at about 4,000 years old, it would ask that that temple was there approximately 10,000 to 12,000 years ago. And eventually I came across these things that were thought to have been popularized now as the flower of life. You can see them again, and so they're high on the pillars. And what's really amazing about this graph, this geometry that's imprinted on the granite, is that it's not cut, it's not etched into the granite, it's burnt into the atomic structure of the granite. It's burnt onto it like if it was laser burnt on the granite. And that poses a very large problem when you're thinking of 10,000 years ago, people going around burning stuff with lasers. Interestingly, when you take this geometry and you extrapolate it into 3D structures, now each circle becomes a sphere. The petals that we were discussing earlier, or the lobes we were discussing earlier, appears, and if you place a tetrahedron in each sphere, you get the 64 tetrahedron grid. The reason I'm mentioning all this is that there's evidence that there's people in this world that were able to do things in a manner that's completely different than how we do things today, and that exceed our capacity to do them today with all of our technology. Maybe, just maybe, because our technology is based on reactive, explosive technologies instead of contractive space-time curvature technologies, which would allow us to control gravitational fields and so on. These higher level of initiation always related, or typically related, to the eye of Horus. And when they use this hieroglyph in their writing, it's interesting to note that when they did, they used each part of the eye for a specific fraction of mathematics, and that each fraction went on towards the 1/64th fraction, which is the dynamics of the division of tetrahedron array in space. We go to the Forbidden City, and at the entrance of the city, typically you have the Sphinx. The Sphinx, both in Egypt and in China and other traditions, is considered the guardian of knowledge and is usually placed at the entrance, and they guard the knowledge. But what's under the paws of this guardian? Well, when you look carefully, he's guarding the knowledge, which is a sphere with the lobes of the geometry of space embedded in it. And again, we find this information just percolating all around the world in these places where there's incredible buildings, incredible amount of knowledge. And, you know, sure enough, these traditions in China are linked to the knowledge of the I Ching and the Yin Yang. And the Yin Yang is the torus viewed from above, as we saw earlier. And then the I Ching is made out of 64 symbols, each symbol being made out of 6 sticks, right? And the way you define each symbol relative to each other is that the sticks are either broken or full. And usually they're arranged in a circle, like so, where 1 is in opposition to 64, 2 is in opposition to 63, 3 is in opposition to 62, and so on.
and each one has the same number of full stick and the same number of broken stick. It's just that they're arranged differently between two pairs. I'm thinking, wait a minute, if I take 6 sticks and I put them together in a geometry, if they're the same length, then the only geometry I can generate out of those 6 sticks is a tetrahedron. And I thought, okay, that kind of works, so maybe the code has to do with tetrahedrons. But what would it be about the broken sticks? What are the broken sticks about? What's going on? Smaller tetrahedrons, what's going on? And it took me a while to figure this out, but eventually I realized that when you follow the code of the I Ching, it goes 164, and they're in opposition. So if you took 1, this is 1 here, and then this is 64, and you put them together, then the sticks have to intersect. And that's why you have the broken sticks, because when they intersect, they get broken. Bang, 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 bang. And here's your star tetrahedron structure. And so you can continue to build the I Ching, okay, and follow the code and continue to build the star tetrahedron structure with the positive and the negative and the positive and the negative. And by the time you're finished, you will have a 512 tetrahedron grid, which is just happens to be in the next fractal level from 64. So then you have all the fractal, progression. It's very important. I mean, these are fundamental beliefs that we have around the world. They're very important traditions that have very important sets of data that are telling us about the structure of space-time, that are telling us about the dynamics of space-time.